The universe is a vast and mysterious canvas, a tapestry woven from threads of light and darkness, of matter and energy, all governed by a set of fundamental rules that we are only just beginning to comprehend. For centuries, our understanding of this cosmic drama has been shaped by four primary actors: the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. These are the pillars of our physical reality, the invisible architects that build everything from the smallest subatomic particle to the largest supercluster of galaxies. But what if the stage is more crowded than we think? What if there are other hidden actors, other fundamental forces waiting in the wings, forces that have been silently shaping the cosmos in ways we have not yet even begun to imagine? This is one of the most exciting and profound questions in all of modern physics, the quest to discover a fifth force. It is a quest that has tantalized and obsessed researchers for decades, a search that could not just add a new chapter to our textbooks, but could fundamentally rewrite our entire understanding of the universe and our place within it. The clues that hint at the existence of these new forces are subtle, ghostly, and often ambiguous. They are found in the strange, anomalous behavior of the cosmos at its largest and its smallest scales. When we look out at the grand spiral galaxies, we see that their outer stars are rotating far too fast, moving with a velocity that should send them flying off into the intergalactic void if the only gravity at play was that of the visible stars and gas. This has led to the hypothesis of dark matter, an invisible but mysterious substance that seems to make up about 27% of the universe's mass energy content. But what if dark matter is not just a passive, inert substance? What if it interacts with itself, or even with us, through a new, undiscovered dark force? Such a force could explain some of the puzzling discrepancies we see in the distribution of dark matter on different scales, and it would mean that the dark sector of the universe is not just dark, but is also home to a rich and complex physics of its own. On an even grander scale, there is the mystery of dark energy, the even more enigmatic force that is causing the expansion of the universe to accelerate. A new fundamental force could be the key to understanding this cosmic anti-gravity. Perhaps a long-range, incredibly weak force that only becomes apparent over the vast, empty distances between the galaxies. The search for these new forces is not just a matter of looking out at the cosmos. It is also a matter of looking in, of probing the very heart of matter in our most powerful particle accelerators. At facilities like the Large Hadron Collider at CERN, physicists are smashing particles together at nearly the speed of light, recreating the extreme energy conditions of the first moments after the Big Bang. In the fiery debris of these collisions, they are searching for new, unexpected particles, for new, subtle interactions, for any deviation from the predictions of our current standard model of particle physics that could be the telltale signature of a new force. The implications of discovering a new fundamental force would be nothing short of revolutionary. It would be a discovery on par with the discovery of electromagnetism or the nuclear forces, a moment that would fundamentally reshape our understanding of the fabric of reality. It could provide the key to a unified theory, the long-sought dream of Einstein to unite all the forces of nature, including gravity, into a single, elegant mathematical framework. Theories like string theory, for example, naturally predict the existence of a host of new forces and particles. String theory posits that the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. The different vibrational modes of these strings correspond to the different particles we see, and the theory requires the existence of extra hidden dimensions of space to be mathematically consistent. These extra dimensions could be the home of new forces, forces that could leak into our familiar three dimensions in subtle and potentially detectable ways. This is a vision of reality that is far richer, more complex, and more multi-layered than our current four-dimensional picture. It is a vision where the world we see is just a shadow, a projection of a much deeper, higher dimensional reality. And the quest to find a new force is, in a sense, a quest to peer into these hidden dimensions, to catch a glimpse of the true, underlying structure of the cosmos. Even our understanding of time itself could be transformed. Some speculative theories suggest that a new force could be linked to the very nature of time's arrow, the unidirectional flow from past to future. The universe is not just a stage for a fixed set of forces. It is a dynamic, evolving cosmos. And the forces of nature themselves may have changed over cosmic history. The search for a fifth force is a journey to the very frontier of our knowledge, a journey that is pushing the limits of our technology, our mathematics, and our very imagination. It is a reminder that the universe is not a closed book that we are close to finishing, but a vast, open library with an infinite number of volumes, most of which we have not even opened yet. The story of our understanding of the cosmos is a story of ever-expanding horizons, a journey that has taken us, in the span of just a few millennia, from a small, Earth-centered world to a vast 14-billion-year-old universe teeming with hundreds of billions of galaxies. This journey began with our most ancient ancestors, with the Babylonians and the Egyptians, who first looked up at the night sky not just with awe, but with a desire to understand. They were the first true astronomers, meticulously charting the motions of the stars and the planets, creating the first calendars, and laying the practical and mathematical groundwork for all that was to come. The ancient Greeks, with their unique gift for philosophical and geometrical inquiry, transformed this observational knowledge into the first comprehensive cosmological models. The geocentric model of Aristotle and Ptolemy, with its elegant, if complex, system of nested crystalline spheres, was a monumental intellectual achievement. A picture of the universe that would dominate Western thought for over 1,000 years. The Islamic world, during the long European Middle Ages, became the custodian and the innovator of this classical knowledge. Astronomers like al-Sufi and al-Battani not only preserved and translated the great works of the Greeks, but they also made their own. Crucial contributions, developing new mathematical techniques, building more precise instruments, and making new observations that would later be a vital resource for the astronomers of the European Renaissance. The great turning point, the Copernican revolution of the 16th century, was a moment when a single, radical idea that the Earth was not the center of the universe began to unravel the entire ancient worldview. This was a revolution that was not just about astronomy. It was a revolution in human thought, a profound and often unsettling decentering of humanity from a privileged place in the cosmos. The work of Johannes Kepler, with his discovery of the elliptical orbits of the planets, and of Galileo Galilei, with his groundbreaking telescopic observations, provided the crucial empirical evidence that would ultimately confirm the Copernican model and consign the ancient geocentric universe to the history books. The final piece of this classical clockwork universe was put in place by the towering figure of Sir Isaac Newton in the late 17th century. His law of universal gravitation was a stunning and powerful unification, a single mathematical principle that could explain both the fall of an apple and the orbit of the moon. It was a vision of a universe governed by precise, predictable, and universal laws, a vision that would define the scientific worldview for the next 200 years. The 19th century saw another great unification, that of electricity, magnetism, and light, in the beautiful and elegant equations of James Clerk Maxwell. This was the dawn of our understanding of the electromagnetic force, and it paved the way for the technological revolutions of the 20th century, But the 20th century would bring its own, even more profound, revolutions. Albert Einstein's theories of special and general relativity shattered the Newtonian concepts of absolute space and time, revealing a much more dynamic and interconnected reality, a four-dimensional space-time that is curved and warped by the presence of matter and energy. At the same time, the development of quantum mechanics was revealing the strange, probabilistic, and deeply counterintuitive nature of the subatomic world. And on the observational front, astronomers like Edwin Hubble were using the new, giant telescopes to discover that our Milky Way was just one of billions of other galaxies, and that these galaxies were all flying away from us, a sign that the universe itself was expanding. This led to the formulation of the Big Bang Theory, the idea that our entire vast cosmos began in an incredibly hot, dense, and singular state some 14 billion years ago. The launch of the first artificial satellite, Sputnik, in 1957 marked the beginning of a new era, the space age, an era where we could finally leave our home planet and begin to explore the cosmos directly. The journey to the moon, with the Apollo 11 mission in 1969, was a moment of profound, collective human achievement, a moment when we first set foot on another world and looked back at our own, fragile, pale blue dot, suspended in the vast, dark emptiness of space. This long and incredible journey of discovery, from the ziggurats of Babylon to the Sea of Tranquility, is a testament to the power of human curiosity, to our relentless and perhaps unique desire to understand our origins, our home, and our place in the grand and still unfolding cosmic story. Our entire vast and complex universe is governed by just four fundamental forces. They are the invisible threads that weave the fabric of reality, the cosmic rules of engagement that dictate how every single particle, from the smallest quark to the largest galaxy, interacts with every other. The first and most familiar of these is gravity. It is, by a huge margin, the weakest of the four forces, but it is also the one with an infinite range. It is a force that is always attractive, a gentle but relentless pull that every particle of matter and energy exerts on every other. It is the force that holds us to the Earth, that holds the Earth in its orbit around the Sun, that holds the Sun in its orbit around the center of the Milky Way, and that holds the billions of galaxies together in the vast, filamentary structures of the cosmic web. In the modern Einsteinian picture, gravity is not a force in the traditional sense, but is the very geometry of space-time, a curvature of the cosmic fabric caused by the presence of mass and energy. The second force is electromagnetism. It is a force that is vastly, unimaginably stronger than gravity. But it comes in two flavors, positive and negative charge, which means that on large scales, it tends to cancel itself out. It is the force that acts between charged particles, and it is responsible for almost all of the phenomena of our everyday lives. It is the force that holds atoms together, that binds molecules in chemical bonds, that gives rise to the structure and the properties of all the materials we see around us. It is the force behind electricity, behind magnetism, and behind light itself, which is a traveling wave of electromagnetic fields. It is a force that is described with exquisite precision by the theory of quantum electrodynamics, one of the most successful and well-tested theories in the entire history of science. The third and fourth forces operate only on the tiny subatomic scales of the atomic nucleus, and they are responsible for the very existence of the elements that make up our world. The strong nuclear force is, as its name suggests, the most powerful of all the forces. It is the superglue of the cosmos, the force that binds the quarks together to form protons and neutrons, and that binds the protons and neutrons together to form the atomic nucleus, overcoming the immense electromagnetic repulsion of the positively charged protons. It has an incredibly short range, operating only over distances smaller than the diameter of a proton. It is described by the theory of quantum chromodynamics. The weak nuclear force is the fourth and final force. It is weaker than both the strong force and electromagnetism, but still much stronger than gravity. It is also a short-range force, and it is responsible for certain types of radioactive decay, like beta decay, a process that is crucial for the nuclear reactions that power the sun. The weak force is the only one of the four that violates certain fundamental symmetries of nature. And this subtle asymmetry may be the key to understanding why our universe is made of matter and not antimatter. These four forces, in their beautiful and complex interplay, are responsible for all the richness and diversity of the universe we see. But the ultimate dream of physics is to find a deeper, underlying unity, a single, elegant theory that can describe all four of these seemingly disparate forces as different manifestations of a single, primordial superforce. We have already had some success in this quest for unification. In the 1970s, the electromagnetic and weak forces were unified into a single electro-weak theory, a discovery that was a major triumph of the standard model of particle physics. The next great step would be to unify the electro-weak force with the strong force, a step predicted by grand unified theories. And the final, ultimate goal, the holy grail of modern physics, would be to unify this grand unified force with gravity, to create a theory of everything. This is the challenge that theories like string theory are attempting to meet. The story of the four fundamental forces is the story of our ongoing quest to read the mind of God, to find the single, elegant, and beautiful set of principles that governs our entire, vast, and wonderful cosmos. The history of physics is, in many ways, a history of a series of profound and revolutionary discoveries that have revealed and then unified the fundamental forces of nature. The journey began in earnest in the 17th century with the work of Sir Isaac Newton. His law of universal gravitation was a moment of breathtaking unification. It revealed that the force that governs the fall of an apple on Earth is the very same force that governs the stately celestial dance of the planets and the moons. It was the first time that the terrestrial and the celestial realms had been brought together under a single mathematical law. For the next 2 centuries, the Newtonian universe, a clockwork cosmos of particles and forces moving in an absolute and separate space and time, reigned supreme. The next great unification came in the 19th century, with the work of a host of brilliant experimentalists and theorists, culminating in the magnificent synthesis of James Clerk Maxwell. He showed that the seemingly separate phenomena of electricity and magnetism were, in fact, two sides of the same coin, two aspects of a single underlying electromagnetic force. His beautiful and compact set of equations not only unified these two forces, but also revealed that light itself is an electromagnetic wave, a discovery that would pave the way for the invention of radio, of television, and of all of our modern but wireless technologies. The early 20th century brought two, even more profound, revolutions that would completely shatter the classical Newtonian worldview. Albert Einstein's special theory of relativity unified space and time into a single, four-dimensional continuum, space-time. And his general theory of relativity unified this space-time with gravity, revealing that gravity is not a force that propagates through space, but is the very curvature of space-time itself. His famous equation, E equals mc squared, revealed a deep and unexpected unity between mass and energy. At the same time, the development of quantum mechanics was revealing the strange, probabilistic, and deeply counterintuitive nature of the subatomic world. This new theory would provide the framework for understanding the two remaining and newly discovered fundamental forces. The strong nuclear force, the force that binds the atomic nucleus together, was first understood through the work of physicists like Hideki Yukawa in the 1930s, and was later given its complete, modern formulation in the theory of quantum chromodynamics. The weak nuclear force, responsible for radioactive decay, was first described by Enrico Fermi and was later incorporated into a unified theory with electromagnetism. This electro-weak unification, developed in the 1960s and 70s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, was a monumental achievement, a triumph of the standard model of particle physics. It showed that at the high energies of the early universe, the electromagnetic and weak forces were indistinguishable, two aspects of a single, underlying electro-weak force. This unification was confirmed with the discovery of the W and Z bosons, the massive force-carrying particles of the weak interaction, at CERN in the 1980s. The standard model is our current and remarkably successful theory of the electromagnetic, weak, and strong forces and all the known elementary particles. It is a beautiful and predictive theory, but it is also an incomplete one. It does not include gravity, and it has a number of arbitrary to free parameters that we do not understand. The quest for a deeper unification continues. Grand unified theories attempt to unify the electro-weak and strong forces into a single, grand unified force. These theories predict that at even higher energies, the quarks and leptons would become indistinguishable, and that the proton, the stable building block of all ordinary matter, should eventually decay, albeit on a timescale that is far longer than the current age of the universe. The final, ultimate unification, the theory of everything, would bring gravity into this unified picture. This is the great, unfinished revolution in physics, the challenge that is being tackled by theories like string theory and loop quantum gravity. The history of our understanding of the fundamental forces is a story of a progressive unification, of a search for a deeper and simpler underlying reality. It is a story that has been written by some of the most brilliant and creative minds in the history of our species. A story that is a testament to the power of the human intellect to comprehend the deep and beautiful order of the cosmos. The development of quantum mechanics in the early 20th century was a revolution that not only changed our understanding of the subatomic world, but also provided a completely new language for describing the fundamental forces of nature. In the classical pre-quantum picture, forces were described as fields, continuous entities that filled all of space. An electric charge, for example, creates an electric field, and another charge feels a force when it is placed in that field. But in the quantum picture, these fields are quantized. They are not continuous, but are made up of discrete, particle-like excitations, or quanta. A force is not a smooth push or pull. It is the result of the exchange of these force-carrying particles. This is the central idea of quantum field theory, the framework that underpins the entire standard model of particle physics. The electromagnetic force, in this picture, is mediated by the exchange of photons, the quantum particles of light. When two electrons repel each other, what is actually happening at a microscopic level is that they are constantly exchanging virtual photons. These photons are virtual because they exist for such a short time, as allowed by the Heisenberg uncertainty principle, that they cannot be directly observed. But their collective effect is the very real and very familiar electromagnetic force. This beautiful and powerful theory, quantum electrodynamics, developed in the mid-20th century by physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, is one of the most precisely tested theories in all of science. The same principle of particle exchange applies to the other forces. The strong nuclear force, which binds the quarks together to form protons and neutrons, is mediated by the exchange of particles called gluons. The theory of the strong force, quantum chromodynamics, is a much more complex and mathematically challenging theory than QED. But it is also a remarkably successful one, explaining why quarks are forever confined within protons and neutrons, and why the strong force becomes weaker at very high energies. The weak nuclear force is mediated by the exchange of two very massive force-carrying particles, the WW and Z bosons. The fact that these particles are so heavy is what makes the weak force so short-ranged. The discovery of the W and Z bosons at CERN in the 1980s was a stunning confirmation of the electroweak theory, which unifies the weak and electromagnetic forces. In this unified picture, the photon and the W and Z bosons are all different manifestations of a single underlying electroweak interaction. The great outstanding puzzle in this quantum picture of the forces is gravity. A quantum theory of gravity would require the existence of a force-carrying particle for the gravitational force, the graviton, but a consistent, mathematically sound theory of the graviton and its interactions has proven to be incredibly elusive. The attempt to apply the standard techniques of quantum field theory to gravity leads to uncontrollable, infinite answers that render the theory useless. This is the central challenge of quantum gravity. Theories like string theory and loop quantum gravity are our best attempts to solve this profound problem. The quantum mechanical picture of forces as the exchange of particles has completely revolutionized our understanding of the universe. It has revealed a hidden, subatomic world of incredible richness and complexity, a world governed by the strange and beautiful laws of probability and uncertainty. And it has provided a powerful and predictive framework for understanding three of the four fundamental forces of nature. The quest to complete this picture, to find a quantum description of gravity, and to unite it with the other forces, is the great unfinished adventure of modern physics. The story of our understanding of gravity is a story of two titans of science, Sir Isaac Newton and Albert Einstein. Newton, in the 17th century, gave us our first comprehensive mathematical theory of gravity. His law of universal gravitation, which states that every particle of matter in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them, was a work of breathtaking genius. It was a single, simple, and elegant law that could explain the fall of an apple, the orbit of the moon, the tides of the oceans, and the stately clockwork motion of the planets. It was a theory that unified the heavens and the earth, showing that they were governed by the same universal laws. Newton's theory of gravity and his three laws of motion would form the bedrock of physics for over 2 centuries. But for all its power and success, Newton's theory had a few subtle, conceptual problems. It described how gravity worked with exquisite precision, but it did not explain why. How did the sun know where the earth was? To exert a force on it, the idea of action at a distance, of a force that could be transmitted instantaneously across the empty vacuum of space, was something that Newton himself found to be deeply unsettling, and there were a few tiny observational discrepancies. The orbit of the planet Mercury, for example, was not behaving exactly as Newton's theory predicted. Its elliptical orbit was slowly precessing, or rotating, at a rate that could not be fully accounted for by the gravitational pull of the other planets. It was a tiny anomaly, a crack in the beautiful Newtonian edifice. And it was this crack that a young patent clerk named Albert Einstein would, in the early 20th century, blow wide open. Einstein's general theory of relativity, published in 1915, was a complete and radical rethinking of the nature of gravity, of space, and of time. In Einstein's picture, gravity is not a force that propagates through space. Gravity is the geometry of space. He proposed that space and time are not a static, passive background, but a dynamic, four-dimensional entity, space-time, that can be bent, curved, and warped by the presence of mass and energy. Massive objects, like the sun, create a deep dip or well in the fabric of space-time around them, and other objects, like the Earth, are not being pulled by a force. They are simply following the straightest possible path, a geodesic, through this curved space-time. It is like a bowling ball placed on a stretched rubber sheet, creating a depression, and a marble rolled nearby, which will then circle the bowling ball, not because it is being pulled by a force, but because it is following the curved contours of the sheet. This is a profound and beautiful idea, and it made a number of new and testable predictions. It correctly predicted the anomalous precession of the orbit of Mercury. It predicted that light itself should be bent by gravity, a prediction that was famously confirmed during a solar eclipse in 1919. And it predicted that time itself should be affected by gravity, that clocks in a stronger gravitational field should run slower than clocks in a weaker one, a phenomenon known as gravitational time dilation, which is a real and measurable effect that must be accounted for in the operation of our GPS satellite system. The discovery of gravitational waves in 2015 by the LIGO Observatory. The detection of the faint, propagating ripples in the fabric of space-time created by the collision of two black holes a billion light-years away was the final, stunning confirmation of Einstein's theory. It is a theory that has passed every experimental test with flying colors, and it remains our best and most complete description of the force that shapes the large-scale structure and the evolution of our entire cosmos. The development of theoretical frameworks is the very heart of the scientific enterprise. A theory is not just a collection of facts or a random guess. It is a coherent, logical, and mathematically consistent structure of ideas that can explain a wide range of observed phenomena and that can make new, testable predictions. In the study of the cosmos, we have two such grand, overarching frameworks: general relativity and quantum mechanics. General relativity, as we have seen, is our theory of the large-scale universe. It is a theory of gravity, of space-time, of the evolution of the cosmos as a whole. Its language is the language of differential geometry, of tensors, and of curved manifolds. Quantum mechanics, on the other hand, is our theory of the small-scale universe. It is a theory of particles, of fields, of the probabilistic and uncertain nature of the subatomic world. Its language is the language of wave functions, of operators, and of Hilbert spaces. These two frameworks are the twin pillars of modern physics, and they are both incredibly successful. But they are built on fundamentally different principles and seem to describe two mutually incompatible realities. The great unfinished quest of theoretical physics is to find a single, deeper framework that can unify these two, a theory of quantum gravity. And in this quest, a number of ambitious and highly speculative theoretical frameworks have been proposed. String theory is perhaps the most famous and well-developed of these. It is a framework that attempts to unify all the particles and forces of nature, including gravity, by positing that the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. The different vibrational modes of these strings give rise to the different particles we observe. String theory is a framework of immense mathematical beauty and power, and it has the potential to solve some of the deepest puzzles in physics, from the nature of black holes to the origin of the universe. But it is also a theory that lives in a world of 10 or 11 space-time dimensions, and it has, so far, failed to make any unique, experimentally testable predictions. Loop quantum gravity is the leading alternative to string theory. It is a more conservative approach that does not try to unify all the forces, but instead focuses on the specific problem of quantizing Einstein's theory of general relativity. In this framework, space-time itself is not a smooth, continuous background, but is made of discrete, quantum atoms of space and time. These atoms are connected in a network called a spin network, and the evolution of this network creates a spin foam. Loop quantum gravity is a beautiful and conceptually radical idea, but it has struggled to show how the familiar smooth space-time of our macroscopic world can emerge from this underlying discrete quantum structure. Beyond these two main approaches, there are a host of other, more speculative, theoretical frameworks being explored. Causal dynamical triangulation is a computer-based approach that tries to build a quantum spacetime from simple, discrete building blocks. Twistor theory, an idea that goes back to Roger Penrose, attempts to describe reality not in terms of points in spacetime, but in terms of more abstract, geometric objects called twistors. Asymptotic safety is a framework that suggests that a quantum theory of gravity might be well-behaved and predictive, even without the need for a full unification with the other forces. These theoretical frameworks are not just abstract, mathematical games. They are the tools that we use to explore the very limits of our understanding. They are the scaffolding upon which we build our picture of the universe. And while they are often highly speculative and far from being experimentally confirmed, they are essential to the progress of science. They are the source of new ideas, of new questions, and of new, unexpected connections. And it is from this vibrant and often chaotic ecosystem of competing theoretical frameworks that the next great revolution in our understanding of the cosmos will, one day, emerge. The idea that there might be more to the universe than the four familiar forces of nature is a tantalizing and recurring one in the history of physics. It is a possibility that is suggested by a number of deep, unresolved puzzles in our current understanding of the cosmos. Puzzles that seem to hint at the existence of a hidden, dark sector of reality, with its own particles and its own forces. String theory, our most ambitious framework for a unified theory, provides a natural and almost profligate home for new forces. In a world of 10 or 11 dimensions, the possibilities for new fields and new interactions are almost limitless. The specific nature of these forces would depend on the precise, and as yet unknown, geometry of the extra compactified dimensions. Some of these forces might be confined to the extra dimensions, while others could leak into our familiar three-dimensional world, their effects manifesting as a modification to gravity or as a new, incredibly weak interaction. The concept of extra dimensions itself, even outside the specific framework of string theory, provides a fertile ground for speculating about new forces. The Kaluza-Klein theory, first proposed in the 1920s, was a remarkable early attempt to unify gravity and electromagnetism by positing the existence of a single, tiny, circular extra dimension of space. In this theory, the electromagnetic force is not a separate, fundamental force, but is simply the manifestation of gravity in this hidden fifth dimension. While this specific model does not work in its simple form, the general idea that new forces can arise from the geometry of extra dimensions remains a powerful and recurring one in modern physics. The mystery of dark matter is another major motivation for the search for new forces. The standard cold dark matter model assumes that dark matter is a single, stable particle that interacts only through gravity and the weak nuclear force. This simple model has been remarkably successful in explaining the large-scale structure of the universe, but it has a number of small, but persistent, problems in explaining the detailed structure of individual galaxies. This has led to the idea that the dark sector may be more complex than we thought. Dark matter may not be a single particle, but a whole family of particles, with its own, new, dark forces that mediate interactions between them. A self-interacting dark matter model, for example, could help to explain why the cores of some galaxies are less dense than the simplest cold dark matter models predict. The mystery of dark energy is another potential signpost to new physics. While the simplest explanation for the accelerating expansion of the universe is a cosmological constant, this comes with the immense theoretical baggage of the vacuum catastrophe. This has led to the exploration of alternative, dynamical dark energy models, like quintessence, which propose that the acceleration is driven by a new, incredibly light scalar field, a field that would be associated with a new long-range fifth force. Even our understanding of gravity itself is not beyond question. Modified gravity theories, like Emond, propose that the law of gravity itself is different on galactic scales, which would explain the anomalous rotation of galaxies without the need for dark matter. While these theories face a number of significant challenges in explaining the full range of cosmological observations, they are a powerful reminder that our current understanding of gravity, as magnificent as it is, may not be the final word. The quest for a theory of quantum gravity is also a search for new forces. In most approaches to quantum gravity, at the incredibly high energies of the Planck scale, the familiar low-energy forces of nature are expected to be unified into a single primordial superforce. And the process by which this unified force breaks down into the four forces we see today as the universe cools and expands could leave behind a host of new, remnant forces and exotic particles. The search for new forces is a search at the very frontiers of our knowledge. It is a search that is guided by the subtle clues and the deep puzzles of our current theories. And it is a search that is being pursued with a host of new and powerful experimental and observational tools. It is a search that may, one day, reveal that the universe we see is just the tip of a much larger and much stranger cosmic iceberg. The framework of string theory, with its vision of a universe built from tiny, vibrating strings and extra, hidden dimensions, is not just a potential theory of everything. It is also a powerful and prolific generator of new, speculative possibilities for the nature of reality, including the existence of new fundamental forces. In the world of string theory, the properties of the particles and forces we observe are not fundamental, but are a consequence of the geometry of the extra compactified dimensions. The way these extra dimensions are curled up, their shape, their size, their topology, determines the allowed vibrational modes of the strings, and therefore the entire particle zoo of our universe. Because string theory allows for a vast landscape of different possible geometries for these extra dimensions. It also allows for a vast landscape of different possible universes, each with its own unique set of physical laws and fundamental forces. In this context, the question is not, are there new forces, but why are the forces we see the only ones? The theory naturally predicts the existence of a host of other fields and forces beyond those of the standard model. Most of these new forces are expected to be either incredibly weak or to operate only over incredibly short distances, which is why we have not yet detected them. For example, the moduli fields that describe the shape and size of the extra dimensions would, if they exist, give rise to new, long-range, gravity-like forces. The fact that we have not observed any such forces puts very tight constraints on these models, but it is possible that these forces are so weak that they have, so far, escaped detection. Another possibility is that some of these new forces are confined to the extra dimensions, or that they only act on the particles of the dark sector, like dark matter. String theory also provides a natural framework for brane cosmology. The idea that our universe is a three-dimensional membrane floating in a higher dimensional bulk. In this scenario, there could be new forces that are mediated by particles that can travel in the bulk, not just on our brane. These bulk forces could have a different distance dependence than our familiar three-dimensional forces, and they could provide a new way for our universe to interact with other parallel brane worlds. The implications of new forces arising from string theory are profound. They could provide a natural explanation for the hierarchy problem, the question of why gravity is so incredibly weak compared to the other forces. In some brain world models, this is because gravity is the only force that is leaking into the large, extra dimensions, which dilutes its strength. New forces could also be the key to understanding the nature of dark matter and dark energy. Dark matter could be a particle that is charged under a new, dark force, but is neutral under our familiar electromagnetic force. Dark energy could be the result of a potential energy between our brain and another, or a manifestation of the complex geometry of the extra dimensions. The search for these new string theory-inspired forces is a major driver of research at the Large Hadron Collider and in a host of other high-precision tabletop experiments. At the LHC, physicists are looking for the direct production of new, heavy particles that could be the carriers of a new force, or for the production of Kaluza-Klein particles, which would be the signature of extra dimensions. The tabletop experiments are searching for tiny, subtle deviations from the known laws of physics, like a violation of the inverse square law of gravity at very short distances, or a new, incredibly weak, long-range force that could be detected by a sensitive torsion balance. So far, no definitive evidence for any of these new forces has been found, but the search continues. String theory, for all its mathematical elegance and its conceptual beauty, remains a purely theoretical framework. It is a magnificent and elaborate castle in the sky, a castle that is still waiting for a single, solid experimental foundation to be placed beneath it. The discovery of a new fundamental force, one that is predicted by, or at least consistent with, the framework of string theory, would be a monumental event. It would be the first tantalizing piece of experimental evidence that we are on the right track, that the strange and beautiful multidimensional world of string theory is not just a mathematical fantasy, but a true description of the deep, underlying reality of our cosmos. The quest for unification, the dream of a single, elegant theory that can explain all the forces and particles of nature, is one of the most powerful and enduring drivers of progress in fundamental physics. It is a quest that is based on a deep and almost aesthetic faith that the universe, at its most fundamental level, is simple, coherent, and beautiful. We have seen how this quest has led to a series of historic unifications, from Newton's unification of celestial and terrestrial gravity, to Maxwell's unification of electricity and magnetism, to the electroweak unification of the Standard Model. But the ultimate unification, the one that would bring the force of gravity into this quantum mechanical family, remains the great unfinished symphony of modern physics. Grand unified theories are the next logical step in this journey. They are a class of theories that attempt to unify the three forces of the Standard Model, the strong, the weak, and the electromagnetic forces, into a single, grand unified force. The central idea of QTs is that at incredibly high energies, energies that existed in the very first moments after the Big Bang, these three forces were indistinguishable. They were all different aspects of a single, underlying interaction, governed by a larger and more symmetric mathematical group. As the universe cooled and expanded, this primordial symmetry was spontaneously broken, and the three forces froze out into the distinct and separate forces we observe today. Guts make a number of dramatic and testable predictions. They predict that the strengths of the three forces, which are very different at the low energies of our everyday world, should all become equal at the grand unification energy. And remarkably, when we extrapolate the measured strengths of the three forces to high energies, using the mathematics of the Standard Model, we find that they do not quite meet at a single point. But if we add the new particles predicted by supersymmetry into the calculation, they meet with stunning precision. This is one of the strongest, albeit indirect, pieces of evidence for both supersymmetry and grand unification. Another major prediction of most GUTs is that the proton, the seemingly stable building block of all ordinary matter, is not, in fact, stable. It should, very rarely, decay into lighter particles. This is because GUTs place the quarks and the leptons into the same unified family, and they predict the existence of new super-heavy particles that can mediate interactions that would turn a quark into a lepton, violating the conservation of baryon number and causing the proton to decay. The predicted lifetime of the proton in these theories is incredibly long, on the order of 10 to the power of 33 years or more, which is why we do not see the matter around us dissolving, but a number of large underground experiments, like the Super Kamiokande detector in Japan, are searching for these incredibly rare proton decay events. A definitive observation of proton decay would be a monumental discovery, a direct confirmation of grand unification. The ultimate unification, of course, would be a theory of everything, a theory that brings gravity into this unified picture. This is the challenge that is being tackled by string theory. In string theory, all the forces and particles of nature arise from the different vibrational modes of a single, fundamental entity, the string. It is, in this sense, the ultimate unified theory. And it is a theory that naturally includes gravity, as one of the vibrational modes of the string corresponds to the graviton. The implications of a successful unification theory would be profound. It would not just be the completion of our scientific picture of the world, it would also give us a new and powerful tool for understanding the very origin of the universe. It could explain the origin of the matter-antimatter asymmetry, the nature of cosmic inflation, and the reason why the universe has the specific properties it does. The quest for unification is a quest to read the first page of the cosmic story, to understand the single, simple, and beautiful seed from which all the complexity and diversity of our universe has grown. The quest for a theory of quantum gravity is the great outstanding challenge at the very frontier of modern theoretical physics. It is the quest to reconcile the two towering and seemingly incompatible pillars of 20th century science, Einstein's general theory of relativity and quantum mechanics. General relativity is our theory of the very large, a theory of gravity, of curved space-time, of the evolution of the cosmos. Quantum mechanics is our theory of the very small, a theory of particles, of fields, of the probabilistic and uncertain nature of the subatomic world. And for most practical purposes, these two theories live in separate, non-overlapping domains. But in certain, extreme corners of the universe, in the infinitely dense singularity at the heart of a black hole, and in the fiery, unimaginably hot and dense crucible of the Big Bang, these two worlds collide. To understand these ultimate frontiers of reality, we need a single, coherent theory that can describe the quantum behavior of gravity itself. The fundamental conflict between the two theories lies in their different conceptions of space-time. In general relativity, space-time is a dynamic, physical entity, a smooth, continuous fabric whose geometry is determined by the distribution of matter and energy within it. In quantum mechanics, as it is currently formulated, space-time is a fixed, static, and absolute background, a passive stage upon which the probabilistic drama of quantum fields unfolds. A theory of quantum gravity must somehow resolve this fundamental tension. It must tell us how to describe a space-time that is both dynamic and quantum. Loop quantum gravity is one of the leading approaches to this profound challenge. It is a direct and, in some sense, conservative attempt to apply the principles of quantum mechanics to Einstein's theory of general relativity. In LQG, the smooth, continuous space-time of general relativity is replaced by a discrete quantum structure. Space itself is not infinitely divisible, but is made of fundamental, indivisible atoms or quanta of space, each with a volume of about the Planck length cubed. These atoms are not located in space, they are space. They are connected together in a dynamic, evolving network called a spin network. The geometry of space, the very notions of distance and volume, are emergent properties of the combinatorial structure of this network. The evolution of this spin network in time creates a spin foam, a quantum history of space-time. Loop quantum gravity is a beautiful and conceptually radical theory. It makes a number of specific and dramatic predictions. It predicts that the singularity at the center of a black hole and the initial singularity of the Big Bang are resolved. In the world of LQG, there are no infinities. When a collapsing star reaches the Planck density, the quantum nature of space-time itself creates a powerful, repulsive force that prevents the formation of a true singularity, leading instead to a quantum bounce. The Big Bang, in this picture, may not have been the beginning of time, but was simply a bounce from a previous, contracting phase of the universe. Loop quantum gravity has had a number of notable mathematical successes, but it also faces significant challenges. It has, so far, struggled to show how the familiar, smooth space-time of our low-energy world can emerge from its underlying discrete quantum structure. And it has not yet been able to incorporate the other forces and particles of the Standard Model into its framework. String theory takes a very different, and in many ways more ambitious, approach. Instead of trying to quantize gravity directly, it starts with the idea of unifying all the forces and particles of nature. As we have seen in string theory, the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings. And one of the vibrational modes of this string naturally corresponds to the graviton, the quantum particle of gravity. In this way, string theory is not just a theory of quantum gravity, it is a candidate theory of everything. But string theory, for all its mathematical elegance, comes with its own significant baggage, including the requirement of extra hidden dimensions of space and the vast landscape of possible solutions. The search for a theory of quantum gravity is a search that is pushing the limits of our scientific imagination. It is a search that is forcing us to question our most basic and deeply held intuitions about the nature of space, of time, of matter, and of reality itself. And it is a search that is, at present, severely hampered by a lack of experimental guidance. The effects of quantum gravity are only expected to become significant at the incredibly high energies and tiny distances of the Planck scale, a regime that is far beyond the reach of our current particle accelerators. And so, for now, the quest for quantum gravity remains a largely theoretical one, a beautiful and complex tapestry of mathematical ideas, a story that is still waiting for its first, crucial, experimental thread to be woven in. But the prize is a great one. A successful theory of quantum gravity would not just be the completion of the 20th century revolution in physics, it would be the beginning of a new one. It would be the key to unlocking the deepest secrets of the cosmos, the key to understanding the origin of the universe, the fate of a black hole, and the ultimate, quantum nature of the fabric of reality itself. In the strange and beautiful world of particle physics, the fundamental forces of nature are understood as the exchange of force-carrying particles, or bosons. But the particles that make up the matter of our universe, the fermions, like quarks and electrons, also play a crucial role in shaping the cosmos. The Standard Model of particle physics is our current, and remarkably successful, theory of all the known elementary particles and their interactions. It is a beautiful and predictive theory, a testament to the power of symmetry and mathematics to describe the fundamental workings of nature. The particles of the Standard Model are divided into two main families, the quarks and the leptons. The quarks are the building blocks of the protons and neutrons that make up the atomic nucleus. They come in 6 flavors: up, down, charm, strange, top and bottom, and they are bound together by the strong nuclear force, which is mediated by the exchange of gluons. The leptons are a family of lighter particles that do not feel the strong force. The most famous lepton is the electron, the particle that orbits the atomic nucleus and is responsible for all of chemistry. The electron has two heavier cousins, the muon and the tau, and each of these three charged leptons has a corresponding neutral and incredibly elusive partner, the neutrino. These are the 12 fundamental matter particles of the Standard Model. They are organized into 3 generations of increasing mass, a pattern that is one of the deep, unexplained mysteries of the theory. The forces are mediated by the gauge bosons, the photon for the electromagnetic force, the W and Z bosons for the weak nuclear force, and the 8 gluons for the strong nuclear force. And the final piece of the Standard Model puzzle is the Higgs boson, a particle associated with the Higgs field, which pervades all of space. It is the interaction with this field that gives the fundamental particles their mass. The Standard Model is a triumph of 20th century physics. It has been tested with incredible precision in countless experiments at particle accelerators around the world, and it has, so far, passed every test with flying colors. But for all its success, we know that it is an incomplete theory. It does not include gravity. It does not explain the nature of dark matter or dark energy. It does not explain the matter-antimatter asymmetry of the universe. And it has a number of arbitrary, free parameters, the masses of the particles, the strengths of the forces that we must measure experimentally, but which the theory cannot explain. The search for physics beyond the Standard Model is one of the primary goals of modern particle physics, and there are a number of tantalizing, albeit inconclusive, hints that such new physics may be just around the corner. The mystery of the neutrino masses, for example, is a direct contradiction of the simple Standard Model, which predicts that neutrinos should be massless. The observation that neutrinos do, in fact, have a small but non-zero mass is the first definitive piece of experimental evidence for physics beyond the Standard Model. The existence of dark matter is another powerful clue. The Standard Model contains no particle that has the right properties to be the dark matter. This suggests that there must be a whole new dark sector of particles and forces that we have yet to discover. Supersymmetry is one of the most popular and well-motivated theoretical frameworks for physics beyond the Standard Model. It proposes a new fundamental symmetry between the two classes of particles, fermions and bosons, and it predicts that every known particle has a heavier superpartner. Supersymmetry can provide a natural candidate for the dark matter particle. It can help to solve some of the deep theoretical problems of the Standard Model, and it is an essential ingredient in most versions of string theory. The search for these superpartner particles is one of the main goals of the Large Hadron Collider. The relationship between the world of particle physics and the world of cosmology has become increasingly deep and intimate. The early universe was the ultimate particle accelerator, a place where the energies were so high that all the particles of the Standard Model, and perhaps many new undiscovered particles, were created in abundance. By studying the faint relic radiation from the Big Bang, the cosmic microwave background, cosmologists can place powerful constraints on the properties of these particles and on the physics of the early universe. The universe itself has become a giant, natural laboratory for particle physics. The quest to understand the fundamental particles and forces of nature is a quest that is being pursued on 2 fronts. The high-energy frontier of particle accelerators and the cosmological frontier of our observations of the universe. It is a quest that is driven by the hope that in the synergy between these 2 frontiers, in the dialogue between the very small and the very large, we will find the clues that will lead us to a new, deeper and more complete understanding of the beautiful and still mysterious quantum universe we inhabit. Our understanding of the universe is not just built from abstract theoretical frameworks. It is grounded in the hard, cold, and often beautiful reality of observational evidence. Astronomy is, at its heart, an observational science. We cannot, for the most part, perform controlled experiments on the stars and the galaxies. We can only watch and listen and collect the faint, ancient light and other forms of radiation that travel to us across the vast, dark emptiness of space. And in the past century, our ability to do this has been revolutionized by a new generation of powerful, and often beautiful, tools of observation. The Hubble Space Telescope, launched in 1990, has become a cultural icon, a symbol of our species' insatiable curiosity. By placing a large 2.4-meter telescope above the blurring effects of the Earth's atmosphere, Hubble has given us a view of the cosmos that is of unprecedented sharpness and depth. It has provided us with stunning, iconic images of everything from the birth of stars in the pillars of the Eagle Nebula to the death of stars in the expanding shells of planetary nebula. It has allowed us to measure the expansion rate of the universe with unprecedented precision, to discover the existence of supermassive black holes at the centers of galaxies, and to take the first, tentative steps in analyzing the atmospheres of planets around other stars. The cosmic microwave background, the faint, relic afterglow of the Big Bang, is another of our most powerful observational probes. This faint, uniform glow of microwave radiation comes to us from all directions in the sky. And it is a snapshot of the universe when it was just 380,000 years old. A series of dedicated space missions, from COBE in the 1990s to WMAP and Planck in the 2000s, have mapped the tiny 1 part in 100,000 temperature fluctuations in the CMB with incredible precision. These fluctuations are the seeds of all cosmic structure, the primordial ripples from which all the galaxies and clusters of galaxies have grown. The detailed statistical properties of these fluctuations have provided a wealth of information about the age, the geometry, and the composition of our universe, and they have provided some of the strongest evidence for the theory of cosmic inflation and the existence of dark matter and dark energy. The discovery of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory has opened up a completely new and revolutionary window onto the universe. We can now not just see the cosmos, but we can also hear it. Gravitational waves are faint, propagating ripples in the fabric of space-time itself, created by the most violent and cataclysmic events in the universe. Like the merger of 2 black holes or 2 neutron stars, the ability to detect these waves is a stunning triumph of experimental physics, and it is allowing us to probe the nature of gravity and the properties of black holes in a completely new and unprecedented way. Planetary exploration through a fleet of robotic emissaries has transformed the planets and moons of our solar system from distant, abstract points of light into real, tangible worlds, each with its own unique geology, atmosphere, and history. The rovers on Mars, from Sojourner to Perseverance, have given us an on-the-ground view of the red planet, revealing a world that was once much warmer and wetter, a world that may have once been hospitable to life. The Cassini mission to Saturn gave us a decade of breathtaking images and data from the ringed planet and its incredible family of moons, including the discovery of a subsurface, liquid water ocean on the tiny, icy moon, Enceladus. The search for exoplanets, planets orbiting other stars, has been another of the great observational revolutions of the past few decades. Space missions like Kepler and TESS have used the transit method to discover thousands of new worlds, revealing that planets are incredibly common in our galaxy, and that many of them are small, rocky, and located in the habitable zone of their star, the region where liquid water could exist on their surface. The study of supernova, the explosive deaths of massive stars, has also provided a crucial piece of the cosmological puzzle. The observation that a particular type of supernova, a type Ia, always has the same intrinsic brightness has allowed astronomers to use them as standard candles to measure the vast distances to other galaxies. And it was the surprising dimness of these distant standard candles that led to the revolutionary discovery of the accelerating expansion of the universe and the existence of dark energy. This rich and diverse tapestry of observational evidence, from the photons of the CMB to the gravitational waves of colliding black holes, is the bedrock upon which our entire modern understanding of the cosmos is built. And it is a tapestry that is constantly growing, constantly being refined, constantly revealing new and unexpected patterns as we build new and more powerful tools to extend our senses and our understanding out into the vast, beautiful, and still mysterious universe. The astronomical phenomena we observe in the cosmos are not just beautiful and awe-inspiring spectacles, they are also powerful, natural laboratories, places where the laws of physics are pushed to their absolute limits, and where the subtle signatures of new, undiscovered forces may be hiding in plain sight. The rotation of galaxies is a prime example. For decades, we have known that the outer stars of spiral galaxies are rotating much too fast. According to Newton's law of gravity, the rotation speed should decrease with distance from the galactic center, in the same way that the outer planets of our solar system orbit the Sun more slowly than the inner ones. But what we observe is that the rotation curves of galaxies are flat. The outer stars are moving just as fast as the inner ones. This discrepancy is one of the primary pieces of evidence for the existence of dark matter. A vast, invisible halo of matter that surrounds the visible galaxy and provides the extra gravitational pull needed to hold it together. But what if there is no dark matter? What if the anomalous rotation of galaxies is a sign that our understanding of gravity itself is incomplete? This is the idea behind modified gravity theories like MOND. These theories propose that on the very large scales of a galaxy, the law of gravity is different, that it becomes stronger at very low accelerations. This would explain the flat rotation curves without the need for any new exotic particles. The debate between dark matter and modified gravity is one of the major ongoing controversies in modern astrophysics. And it is a debate that is ultimately about whether the anomalies we see are a sign of a new substance or a new force. Gravitational waves, the faint ripples in space-time, are another powerful tool in the search for new physics. Einstein's general theory of relativity makes very precise predictions about the properties of the gravitational waves that should be emitted by events like the merger of two black holes, by comparing the detailed chirp signal detected by observatories like LIGO with the predictions of the theory. We can perform incredibly precise tests of general relativity in the strong field regime, where gravity is incredibly powerful. So far, Einstein's theory has passed every test with flying colors. But as the sensitivity of our detectors improves, we may begin to see subtle deviations from the predictions, deviations that could be the signature of a new long-range force, or the effect of extra hidden dimensions of space. The explosive deaths of massive stars, supernova, are another place where new forces could leave their mark. The core collapse of a massive star is an incredibly complex event, involving a delicate interplay between gravity, nuclear physics, and the physics of neutrinos. Our current computer simulations of supernovae still struggle to reliably reproduce the observed explosions. It is possible that this is simply because our models are not yet sophisticated enough to capture all the complex, three-dimensional hydrodynamics of the collapsing core. But it is also possible that there is a missing ingredient, a new particle or a new force that plays a crucial role in re-energizing the stalled shockwave and driving the explosion. The cosmic rays, the high-energy particles that constantly rain down on the Earth from space, are another potential messenger of new physics. Some of these particles have energies that are far beyond anything we can create in our terrestrial particle accelerators. The mechanisms that can accelerate particles to these ultra-high energies are still not fully understood, and they may involve new, exotic astrophysical objects or new, fundamental particle interactions. The detailed energy spectrum and composition of these cosmic rays could hold the key to unlocking these mysteries. The cosmic microwave background, the relic radiation from the Big Bang, is perhaps our most pristine and powerful probe of the fundamental laws of nature. The tiny temperature and polarization fluctuations in the CMB are a direct snapshot of the quantum fluctuations that were present in the very first moments of the universe's existence. The statistical properties of these fluctuations are incredibly sensitive to the physics of the early universe. Any new particles, any new forces, any deviation from the standard cosmological model that was present at that time would have left its subtle imprint on the patterns we see in the CMB today. By comparing our increasingly precise maps of the CMB with the predictions of different theoretical models, we can place powerful constraints on a wide range of new physics, from the properties of dark matter and dark energy to the nature of cosmic inflation. The universe is a vast and complex laboratory, and the astronomical phenomena we observe are the results of its ongoing experiments. And by carefully and patiently observing these phenomena, by looking for the subtle anomalies, the small discrepancies, the results that do not quite fit our expectations, we can hope to find the clues that will lead us to a new, deeper, and more complete understanding of the fundamental forces that shape our cosmic home. The intertwined mysteries of dark matter and dark energy, the two dominant and completely unknown components of our universe, are a profound and humbling testament to the vastness of our own ignorance. They are a sign that the beautiful and successful edifice of our current standard model of cosmology, for all its power and its predictive success, is built on a foundation that is 95% mysterious. Dark matter, the invisible scaffolding of the cosmos, makes up about 27% of the universe's mass energy content. We cannot see it, but we can feel its gravitational presence everywhere. It is the unseen hand that holds our galaxy together, that shapes the large-scale structure of the cosmic web, and that bends the light of distant galaxies in the cosmic funhouse mirrors of gravitational lensing. The leading hypothesis is that dark matter is a new, stable, and weakly interacting elementary particle, a WIMP, that was created in the hot, dense conditions of the early universe and has been gravitationally clumping ever since. But despite decades of searching, in deep underground detectors, in our most powerful particle accelerators, and in the signals from space, we have, so far, found no direct evidence for such a particle. This has led to a growing interest in alternative possibilities. Perhaps dark matter is not a WIMP, but a much lighter, wave-like particle called an action. Or perhaps it is not a single particle, but a whole dark sector of particles with its own new dark forces. This would mean that the universe we see, the universe of the standard model, is just one of two parallel and largely non-interacting worlds, a world of light and a world of darkness that are connected only through the gentle, universal touch of gravity. Dark energy is even more mysterious. It is the dominant component of the universe, making up about 68% of its total energy, and it is the source of the strange, repulsive force that is causing the expansion of the universe to accelerate. The simplest explanation for dark energy is that it is the cosmological constant, the intrinsic zero-point energy of the quantum vacuum itself. But as we have seen, this explanation comes with the immense theoretical baggage of the vacuum catastrophe, the 120 orders of magnitude discrepancy between the theoretical prediction and the observed value. This has led to a host of alternative and more exotic possibilities. Perhaps dark energy is not a constant, but a dynamic quintessence field, a field that is slowly evolving over cosmic time. Or perhaps it is a sign that our understanding of gravity itself is incomplete, that general relativity needs to be modified on cosmological scales. The connection between these two, great, dark mysteries, is one of the most compelling and tantalizing questions in modern cosmology. Is it just a coincidence that the energy densities of dark matter and dark energy are of the same order of magnitude in the present epoch of the universe? This coincidence problem has led to the speculation that the two may be connected, that there may be a direct interaction or energy exchange between the dark matter and the dark energy fields. This would be a profound discovery, as it would imply the existence of a new, fifth fundamental force of nature, a force that operates primarily in the dark sector. The search for the nature of dark matter and dark energy is a search that is being pursued on all fronts, from the smallest scales to the largest. It is a search that is pushing the boundaries of our technology, of our theories, and of our very imagination. And it is a search that will, when it is finally successful, not just fill in the missing 95% of our cosmic inventory, but will likely trigger a new and profound revolution in our understanding of the fundamental laws of nature, of the origin and the ultimate fate of our universe, and of the deep, dark, and beautiful mystery that lies at the heart of our cosmic home. The cosmic rays, the constant invisible rain of high-energy particles that bombard the Earth from outer space, are a unique and powerful messenger from the most extreme and violent corners of the universe. They are the debris from cosmic cataclysms, the shrapnel from stellar explosions, the particles that have been accelerated to near light speed in the magnetic chaos of active galactic nuclei. And in the detailed properties of this cosmic radiation, in the subtle anomalies and the unexpected patterns, we may be seeing the first, faint hints of new, undiscovered forces of nature. One of the most significant and long-standing of these anomalies is the positron excess. The alpha magnetic spectrometer, a sophisticated particle detector mounted on the International Space Station, has been meticulously measuring the composition of cosmic rays for over a decade. And it has confirmed, with unprecedented precision, a puzzling and unexpected feature at high energies. There are significantly more positrons, the antimatter counterparts of electrons, than our standard models of cosmic ray production and propagation can explain. Our standard picture is that most of the positrons in cosmic rays are secondary particles, produced when primary cosmic rays, like protons, collide with the atoms of the interstellar medium. But this process cannot account for the observed rising fraction of positrons at high energies. This suggests that there must be an additional primary source of high-energy positrons. One possibility is that this source is astrophysical. Nearby pulsars, the rapidly spinning, highly magnetized remnants of massive stars, are thought to be powerful particle accelerators, and they could be a significant source of high-energy electron-positron pairs. But another, more exciting, possibility is that the positron excess is a sign of new physics. In many models of dark matter, the dark matter particles can annihilate with each other, producing a shower of standard model particles, including electrons and positrons. A large concentration of dark matter, like the one at the center of our own galaxy, could be a powerful, and previously unaccounted for, source of high-energy positrons, a source that could explain the observed excess. A definitive detection of such a signal would be a monumental discovery, our first, indirect glimpse of the dark matter particle and its interactions. Another intriguing puzzle is the origin of the ultra-high-energy cosmic rays, particles with energies that are millions of times greater than anything we can achieve in our most powerful terrestrial particle accelerators. The sources of these particles are a complete mystery. They are so energetic that they should be deflected very little by the magnetic fields of our galaxy, which means they should point back to their sources. But when we look in the directions from which they came, we see no obvious, powerful astrophysical accelerators. This has led to a host of speculative, top-down models for their origin, Perhaps they are not accelerated at all, but are the decay products of some new, super heavy, and incredibly long-lived particle, a relic from the very early universe. Or perhaps they are the signature of a new, exotic astrophysical object, like a network of cosmic strings. Another anomaly lies in the behavior of muons, the heavy cousins of the electron. A number of experiments have reported a significant excess of muons in the particle showers that are created when high-energy cosmic rays hit the Earth's atmosphere. Our standard models of particle physics struggle to explain this muon excess. It may be a sign that our understanding of the strong nuclear force at these very high energies is incomplete, or it may be a hint of new, undiscovered particles or interactions that are being produced in these collisions. These cosmic ray anomalies are subtle, complex, and often contentious. They are at the very edge of our experimental capabilities, and it is always possible that they are the result of some subtle, instrumental effect or a misunderstanding of the complex. Astrophysical environments through which the cosmic rays travel, but they are also a powerful and important part of the scientific process. It is in these anomalies, in these places where the data does not quite fit our models, that the seeds of a new discovery are often sown. The cosmic rays are a free and incredibly powerful particle beam, a gift from the cosmos that allows us to probe the laws of nature at energies that are far beyond our terrestrial reach. And by patiently and carefully studying the messages they bring, we may one day find the first definitive clue that will lead us beyond the familiar territory of our current understanding and out into the new and undiscovered country of a deeper and more complete theory of the universe. The detection of gravitational waves in 2015 by the LIGO and Virgo collaborations was a moment of profound scientific and human achievement. It was the confirmation of a century-old prediction of Einstein's general theory of relativity, the culmination of a multi-decade and often frustrating experimental quest, and the opening of a completely new and revolutionary window onto the universe. For the first time, we could not just see the cosmos, but we could also hear the faint, propagating ripples in the fabric of space-time itself, and in the beautiful and incredibly informative chirp of these gravitational wave signals. We have a new and powerful tool in the search for new, fundamental forces. General relativity makes very precise and specific predictions about the properties of the gravitational waves that should be emitted by an event like the merger of two black holes. The theory predicts the exact shape of the waveform, the way its frequency and amplitude evolve as the two objects spiral into each other, merge, and then settle down into a single, final black hole. By comparing the observed signal with the predictions of the theory, we can perform incredibly precise tests of general relativity in the strong field regime, where gravity is incredibly powerful and space-time is highly curved. And so far, Einstein's theory has passed every test with flying colors. The observed waveforms match the predictions of general relativity with exquisite precision. But as the sensitivity of our detectors improves, and as we begin to collect a larger and more diverse sample of gravitational wave events, we may begin to see subtle deviations from these predictions, and these deviations could be the telltale signature of new physics. For example, some theories that propose a new fifth fundamental force predict that a binary system of two massive objects should lose energy not just to gravitational waves, but also to the radiation of this new force. This would cause the two objects to spiral into each other slightly faster than general relativity predicts, and it would leave a subtle, but potentially detectable, imprint on the early part of the gravitational wave signal. Other theories, like those with extra hidden dimensions of space, predict that gravitons, the quantum particles of gravity, could leak into these extra dimensions. This would cause the amplitude of the gravitational waves to decrease with distance in a way that is different from the standard inverse distance law of our familiar three-dimensional world. by comparing the observed strength of a gravitational wave signal with the estimated distance to its source. We can place powerful constraints on the existence of these extra dimensions. Gravitational waves can also be used to probe the nature of dark energy. The standard cosmological model assumes that dark energy is a cosmological constant, and that gravitational waves travel at the speed of light. But in some alternative, modified gravity theories, which attempt to explain the cosmic acceleration without dark energy, the speed of gravitational waves can be different from the speed of light. The observation in 2017 of both the gravitational waves and the electromagnetic light from the merger of two neutron stars, and the fact that these two signals arrived at Earth at almost exactly the same time after traveling for over 100 million light-years, has placed incredibly tight constraints on this class of modified gravity theories. A beautiful example of the power of multi-messenger astronomy. The ultimate goal of gravitational wave astronomy is to detect the stochastic background of gravitational waves from the very early universe. The faint primordial hiss of spacetime itself, left over from the cataclysmic event of cosmic inflation. The detection of this background and the detailed measurement of its properties would be a discovery of monumental importance. It would be a direct confirmation of inflation, and it would give us a glimpse of the universe at energies that are 1 trillion times higher than those of the Large Hadron Collider. It would be a window into the physics of grand unification, of string theory, of the very birth of the fundamental forces of nature. The search for new forces with gravitational waves is still in its infancy. But it is a field of immense promise. The universe is a symphony of vibrations, of both electromagnetic and gravitational waves, and by learning to listen to both parts of this cosmic music, we are gaining a new, and much richer, and more complete picture of the deep, and still mysterious, laws that govern our cosmos. The cosmic microwave background, the faint, relic afterglow of the Big Bang, is our most precious and informative fossil from the early universe. It is a snapshot of the cosmos when it was just 380,000 years old. A baby picture that has allowed us to determine the age, the geometry, and the composition of our universe with incredible precision. And in the subtle, and seemingly random, pattern of its temperature and polarization fluctuations, we have a powerful and versatile tool in the search for new fundamental forces and new physics beyond the standard model. The statistical properties of these fluctuations are a direct probe of the physics of the primordial universe. The standard model of cosmology, the lambda CDM model, which is based on the theory of cosmic inflation, makes very specific and precise predictions about what these statistics should look like. And so far, the observed CMB, as mapped by missions like WMAP and Planck, has been in stunningly good agreement with the predictions of this simple 6-parameter model. But as our measurements have become more and more precise, a few subtle and tantalizing anomalies have begun to emerge, hints that there may be more to the cosmic story than our standard model allows. For example, some studies have reported a slight, but statistically significant, lack of power in the temperature fluctuations on the very largest angular scales, a feature that is not easily explained by the simplest models of inflation. Others have pointed to a strange, and as yet unexplained, alignment of the largest features of the CMB with the geometry of our own solar system, the axis of evil, as it has been provocatively nicknamed. And there is the cold spot, a particularly large and cold region of the CMB that is statistically unlikely to be a simple, random fluctuation. These anomalies are still a matter of intense debate in the cosmological community. They may be nothing more than statistical flukes, the result of our human tendency to see patterns in random noise, or they may be a sign of some subtle, systematic error in our data or our analysis. But they may also be the first, faint whispers of new physics. The CMB is an incredibly sensitive probe of the number and the properties of the light, relativistic particles that were present in the early universe. The number of effective neutrino species, as it is known, can be precisely measured from the CMB data. The current measurement is in excellent agreement with the 3 known neutrino species of the Standard Model. But if there were a new light particle, a dark photon, or a sterile neutrino, that was present in the early universe, it would have left its subtle imprint on the CMB. An imprint that future, more precise, measurements could detect. The detailed polarization patterns of the CMB are another powerful window into new physics. The polarization of the CMB is created by the scattering of photons off of electrons in the primordial plasma. These polarization patterns come in 2 types, E modes, which are curl-free, and B modes, which have a swirling, vortex-like pattern. The Standard Model of Cosmology predicts that there should be a certain level of E-mode polarization, and this has been observed with high precision. But it also predicts that there should be a much fainter, and as yet undetected, background of B-mode polarization, created by the primordial gravitational waves from cosmic inflation. The search for these primordial B-modes is one of the holy grails of modern cosmology. A definitive detection would be a smoking gun confirmation of inflation, and the strength of the signal would tell us about the energy scale at which inflation occurred, giving us a direct glimpse of the physics of grand unification. But B-modes could also be a sign of more exotic, new physics. Some theories that propose a new fundamental scalar or vector field in the early universe predict that this field could have generated its own unique pattern of B-mode polarization. And some theories that violate the fundamental symmetry of parity predict a correlation between the temperature and the B-mode polarization of the CMB, a signal that is strictly forbidden in the Standard Model. The CMB is a rich and complex tapestry of information, a cosmic Rosetta Stone that is allowing us to decipher the language of the early universe. And as we learn to read this ancient text with ever-increasing precision, with new and more powerful telescopes, both on the ground and in space, we may find that it contains not just the story of our known universe, but also the first, tantalizing clues of a new and even deeper chapter in the cosmic story. The quest to discover new fundamental forces is not just a matter of passive observation. It is also a story of active and often ingenious experimental design. While the high-energy frontier of particle accelerators and the cosmological frontier of our observations of the universe are powerful and important avenues of research, there is a third, and increasingly vibrant, frontier in this search, the precision frontier of small-scale, high-precision, tabletop experiments. These experiments are not trying to create new particles by smashing things together at incredible energies. Instead, they are trying to detect the incredibly subtle and often fleeting effects of new forces by making measurements of familiar, low-energy systems with an unprecedented degree of precision. It is a search for the tiny, unexpected tremor in the fabric of reality that could be the sign of a new, hidden world. One of the classic, and still ongoing, examples of this approach is the search for a violation of the inverse square law of gravity at very short distances, Newton's law of gravity, and Einstein's general relativity. Both predict that the gravitational force between two objects should fall off precisely as the square of the distance between them. But many theories that propose new forces, particularly those with extra hidden dimensions, predict that at very short distances, typically on the scale of millimeters or less, there should be a deviation from this law. This is because, at these short distances, gravity would no longer be a purely three-dimensional force. It would begin to leak into the extra dimensions, changing its strength and its distance dependence. A number of incredibly sensitive experiments, using a device called a torsion balance, have been built to search for such a deviation. These experiments involve measuring the tiny, gravitational-like force between two carefully arranged test masses at sub-millimeter separations. So far, no deviation from the inverse square law has been found, which has placed very tight constraints on many of these theories. But the experiments are constantly being improved, pushing the limits of our knowledge ever deeper into the realm of the very small. Another related class of experiments is the search for a new long-range fifth force that is incredibly weak and that couples to matter in a way that is different from gravity. Some theories, for example, predict the existence of a new force that couples not to mass, but to baryon number or lepton number. Such a force would cause a tiny, composition-dependent violation of the weak equivalence principle. The cornerstone of general relativity, which states that all objects should fall with the same acceleration in a gravitational field, regardless of their composition. A number of highly sensitive Eötvös experiments, which compare the acceleration of two test masses made of different materials in the gravitational field of the Earth or the Sun, have been built to search for such a violation. So far, the equivalence principle has held up with stunning precision, but the search continues. The quantum realm also provides a fertile ground for high-precision tests of fundamental physics. The anomalous magnetic moment of the electron and the muon, a tiny quantum correction to their magnetic properties, is one of the most precisely measured quantities in all of science. And it is also one of the most precisely calculated quantities in the Standard Model. The comparison between the experimental measurement and the theoretical prediction is a powerful test of the completeness of the Standard Model. Any discrepancy could be a sign of the virtual effects of new undiscovered particles or forces. And in fact, for the muon, there has been a long-standing and recently strengthened discrepancy of about 4 standard deviations between the experimental value and the theoretical prediction. This muon G2 anomaly is one of the most tantalizing hints of new physics that we currently have. These tabletop of precision experiments are the unsung heroes of the search for new forces. They may not have the glamour of a giant particle accelerator or a space telescope, but they are a crucial and complementary part of the scientific process. They are a testament to the power of human ingenuity to devise clever and sensitive ways to probe the deepest secrets of nature, not by brute force, but by the patient, meticulous, and beautiful art of precision measurement. And it may be in the tiny, almost imperceptible signal from one of these small, quiet experiments in a university basement somewhere that the first definitive evidence of a new fundamental force of nature will one day be found. The Large Hadron Collider at CERN is more than just the largest and most powerful particle accelerator ever built. It is a veritable discovery machine, a tool of unprecedented power in our quest to understand the fundamental constituents of matter and the forces that govern them. It is our most powerful microscope, allowing us to peer into the subatomic world with an energy and a resolution that is far beyond anything that was possible before. And in the fiery, miniature Big Bangs that are created when two protons collide at nearly the speed of light, we are searching for the telltale signatures of new, undiscovered forces of nature. The most direct way to search for a new force at the LHC is to look for the production of a new, heavy force-carrying particle. In the same way that the discovery of the W and Z bosons in the 1980s was a direct confirmation of the electroweak theory, the discovery of a new heavy Z' boson or a W' boson would be a smoking gun signature of a new fundamental force. These new particles would be unstable, decaying almost instantly into more familiar, standard model particles like electrons, muons, or jets of quarks. The signature of such a discovery would be a bump in the energy distribution of these decay products, a peak at a specific mass corresponding to the mass of the new particle. The ATLAS and CMS experiments at the LHC have been searching for such bumps across a wide range of possible masses and decay channels. So far, no definitive discovery has been made, which has placed very tight constraints on the existence of many of the simplest models of a new force. But the search continues, and with the ongoing high-luminosity upgrade of the LHC, the sensitivity of these searches will be dramatically increased in the coming years. Another, more indirect, way to search for new forces is to look for their effects on the behavior of the known. Standard model particles. The existence of new forces, or of new heavy particles, can lead to subtle but measurable deviations from the predictions of the standard model in the rates of certain rare processes or in the detailed, angular distributions of the particles produced in a collision. These precision measurements are a powerful way to probe for new physics at energy scales that are even higher than the direct reach of the collider. The discovery of the Higgs boson at the LHC in 2012 was a monumental triumph for the Standard Model, the confirmation of its final missing piece. But the Higgs is not just the end of an old story. It may also be the beginning of a new one. The Higgs boson is a unique and mysterious particle, and it may be our most powerful portal to the physics that lies beyond the Standard Model. By precisely measuring the properties of the Higgs, its mass, its spin, its couplings to the other particles, we can search for any deviation from the predictions of the Standard Model. A small discrepancy could be a sign that the Higgs is not a simple, elementary particle, but is a composite object, or that it is part of a larger, more complex Higgs sector with multiple Higgs bosons, as predicted by theories like supersymmetry. The Higgs could also be our window into the dark sector. If there is a new force that communicates between our world and the world of dark matter, the Higgs boson could be the portal through which this interaction takes place. This could lead to a new and previously invisible decay mode for the Higgs, where it decays into a pair of dark matter particles. The signature of such an event at the LHC would be missing energy, as the dark matter particles would fly out of the detector without leaving a trace. The search for these invisible Higgs decays is one of the most exciting and important parts of the LHC's ongoing research program. The Large Hadron Collider is a magnificent and complex machine, a testament to what humanity can achieve when it unites in the pursuit of fundamental knowledge. And while it has, so far, provided a stunning confirmation of our current standard model of particle physics, the story is far from over. The data it is collecting is a vast and largely unexplored territory, and within it, the clues that will lead us to the discovery of a new, fundamental force of nature may be patiently waiting, hidden in plain sight. The vast, dark, and empty spaces of the cosmos are not the only places where we can search for the subtle signatures of new fundamental forces. Our own galactic backyard. The increasingly crowded and complex environment of near-Earth space is also a laboratory for fundamental physics, and the growing fleet of satellites that we have placed in orbit around our planet are not just tools for communication, for navigation, and for observing the Earth. They are also incredibly sensitive, and often unwitting, detectors of the deep, underlying laws of nature. Satellite experiments have played a crucial role in testing the foundations of our understanding of gravity. The LaGOS satellites, for example, are simple, passive, and incredibly dense spheres covered with corner-cube retroreflectors. By bouncing laser beams off of these satellites from ground stations and precisely measuring the round-trip travel time, we can track their orbits with millimeter-scale precision. This has allowed for incredibly precise tests of general relativity, including the measurement of frame dragging, the subtle twisting of space-time around a rotating body like the Earth. Any deviation from the predictions of general relativity in these precise orbital measurements could be a sign of a new, long-range fifth force. The Gravity Probe B mission was another, beautiful, and incredibly challenging satellite experiment designed to test two of the key predictions of general relativity. It used 4 ultra-precise, and cryogenically cooled gyroscopes to measure the curvature of space-time around the Earth and the frame-dragging effect. The results were in perfect agreement with Einstein's theory, providing another powerful confirmation of its validity. Satellites are also powerful tools in the search for dark matter. The alpha magnetic spectrometer on the International Space Station, as we have seen, is making incredibly precise measurements of the composition of cosmic rays. A definitive detection of an excess of antimatter particles, like positrons or antiprotons, that could be unambiguously attributed to the annihilation of dark matter particles in our galactic halo, would be a revolutionary discovery. Other satellite missions, like the Fermi Gamma Ray Space Telescope, are searching for the gamma rays that should be produced in these dark matter annihilation events. By searching for a faint, diffuse glow of gamma rays from the center of our galaxy, or from nearby dwarf galaxies that are thought to be rich in dark matter. These experiments are placing powerful constraints on the properties of the dark matter particle. The cosmic microwave background, our most powerful cosmological probe, has also been mapped with exquisite precision by a series of dedicated satellite missions, from COBE to WMAP and Planck. These satellites have given us a baby picture of our universe, and in the detailed statistical properties of this picture, we can search for the subtle imprints of new physics. A future, dedicated CMB polarization satellite, like the proposed Lightbird mission, would be a powerful tool in the search for the primordial gravitational waves from cosmic inflation. A discovery that would give us a direct glimpse of the universe at the incredible energies of grand unification, the very energies where new forces of nature are expected to emerge. The near-Earth space environment is a unique and valuable laboratory. It is a place where we can perform controlled, high-precision experiments on a scale that is impossible on the ground. And as our technology for building and for operating satellites becomes more and more sophisticated, we will be able to use this laboratory to probe the fundamental laws of nature with an ever-increasing precision, searching for the tiny, subtle clues that will lead us to a new and deeper understanding of the forces that shape our cosmos. The quest to discover new fundamental forces is a quest that is being pursued on all fronts, from the high-energy collisions of particle accelerators to the high-precision measurements of tabletop experiments, to the vast cosmic scales of our astronomical and cosmological observations, and to decipher the subtle clues that are emerging from all of these different frontiers. We need a new and more powerful set of theoretical tools. The development of these tools is one of the most vibrant and exciting areas of modern theoretical physics. At the heart of this effort is the ongoing quest to move beyond the standard model of particle physics. The standard model, for all its success, is an incomplete theory. It is a beautiful and predictive description of the known particles and forces, but it leaves many of the deepest questions of fundamental physics unanswered. And so, a whole ecosystem of theoretical frameworks has been developed to try and address these questions and to provide a structure for our search for new forces. Supersymmetry, as we have seen, is one of the most well-motivated and deeply studied of these frameworks. It provides a natural candidate for the dark matter particle. It helps to solve some of the deep theoretical problems of the standard model. And it is an essential ingredient in most versions of string theory. And it predicts a host of new particles and new interactions that we can search for at the LHC. Theories with extra dimensions are another, powerful and recurring. Theme. These theories, from the simple Kaluza-Klein idea to the complex multidimensional world of string theory, provide a natural and geometric origin for new forces. The search for the signatures of extra dimensions, either through the production of Kaluza-Klein particles at the LHC or through the search for a deviation from the inverse square law of gravity at short distances, is a major focus of experimental physics. Grand unified theories are another important class of theoretical models. They provide a beautiful and compelling framework for unifying the strong, weak, and electromagnetic forces, and they make the dramatic prediction of proton decay, a prediction that is being tested in large, underground detectors. The theoretical implications of a discovery of a new force would be profound. It would not just be about adding a new particle or a new term to our equations. It would be a moment of deep conceptual realignment. It would force us to rethink our most basic assumptions about the structure of the universe, about the nature of symmetry, about the origin of the forces we see. It would be a clue, a signpost, a breadcrumb that would lead us down a new and previously unknown path towards a deeper and more complete understanding of the cosmos. The process of theoretical physics is a constant, and often beautiful, dialogue between mathematics and observation. The theorists, guided by principles of symmetry, of elegance, and of mathematical consistency, propose new ideas, new frameworks, new possibilities. And the experimentalists, with their ingenious and ever more powerful tools, go out and test these ideas against the hard, cold reality of the physical world. It is in this dynamic, creative, and often messy interplay between theory and experiment that scientific progress is made. And as we stand on the threshold of a new era of discovery, with a new generation of powerful experiments and observatories coming online, the prospects for a breakthrough, for the discovery of a new, fundamental force that will forever change our picture of the universe, have never been brighter. The universe is a deep and still largely unread book, and we are, for the first time in our history, beginning to learn how to decipher its most fundamental and beautiful language. The discovery of a new, fundamental force of nature would not just be a revolution in physics, it would be a revolution in our entire human worldview. It would be a moment of profound, and perhaps unsettling, reorientation, a moment when our map of reality is suddenly and irrevocably redrawn. The four forces we currently know, gravity, electromagnetism, and the two nuclear forces are the pillars of our scientific understanding of the world. They are the basis for our technology, our chemistry, our biology, our cosmology. They are the rules of the game. A fifth force would not just be a new rule, it would be a sign that the game itself is far larger and far stranger than we had imagined. The immediate impact would be on the field of particle physics. The standard model, our beautiful and successful, but ultimately incomplete, theory of the fundamental particles and forces would be superseded. The discovery of a new force would provide the crucial experimental clue that would guide us towards a more complete and more fundamental theory, whether that be supersymmetry, or a theory with extra dimensions, or something else entirely that we have not yet even dreamed of. It would be the beginning of a new standard model. The impact on cosmology would be equally profound. A new force could be the key to unlocking the twin mysteries of dark matter and dark energy. If the new force is a dark force that communicates between the particles of the dark sector, it would open up a whole new realm of dark chemistry and dark physics. If the new force is a long-range, gravity-like force, it could explain the accelerating expansion of the universe without the need for a cosmological constant. A new force could also have played a crucial role in the very first moments of the universe's existence, in the process of cosmic inflation, or in the origin of the matter-antimatter asymmetry. The discovery of a new force would give us a new tool, a new lens, through which to view our cosmic history. But the implications would not just be theoretical. A new force could, in the long run, have profound practical applications. The history of physics is a history of fundamental discoveries leading to transformative technologies. The discovery of electromagnetism gave us electricity, radio, and computers. The discovery of the nuclear forces gave us nuclear power and nuclear medicine. What new technologies might a new force enable if the force could be harnessed? Could it lead to new forms of energy, of propulsion, of communication? These are speculative questions, but they are the kind of questions that a fundamental discovery inevitably raises. And the philosophical implications would be perhaps the most profound of all. A new force would be a stark and powerful reminder of the provisional nature of our own knowledge. It would be a lesson in intellectual humility, a reminder that the reality we perceive with our senses and the reality we describe with our current theories is not the whole of reality. It would be a sign that the universe is, and perhaps always will be, more mysterious, more complex, and more wonderful than our current understanding. It would challenge our sense of our own place in the cosmos. The discovery of a new force would be a moment of deep, human connection to the universe. It would be a moment when we, as a species, have listened carefully enough to the cosmos to hear a new and previously unheard note in its grand and ongoing symphony. It would be a moment of awe, of wonder, and of a renewed sense of our own privileged and beautiful place as the part of the universe that is, for now, doing the listening. The existence of new forces would not just add a new chapter to our physics textbooks. It could fundamentally reshape the very structure and the evolution of the cosmos, creating a universe that is far richer, more dynamic, and more complex than the one described by our current four-force model. Imagine, for example, a new long-range force that is repulsive for matter and attractive for antimatter. Such a force, if it existed, could have had a profound impact on the early universe. It could have led to a large-scale separation of matter and antimatter, creating vast domains of the universe that are dominated by one or the other. Our observable universe, with its overwhelming dominance of matter, might just be one, small, matter-dominated domain in a much larger cosmos that is, on average, symmetric. This would be an elegant solution to the matter-antimatter asymmetry problem. Or imagine a new force that couples to dark matter. This dark force could cause the dark matter particles to self-annihilate or to decay, producing a faint, diffuse glow of gamma rays or other standard model particles that we could detect with our telescopes. Or it could be a repulsive force, preventing the dark matter from clumping together too densely in the centers of galaxies, which could explain some of the observed discrepancies with the simplest cold dark matter models. The existence of a dark force would mean that the dark sector of the universe is not just a simple, inert and gravitationally acting substance, but is a rich and complex world of its own, with its own dark chemistry and its own dark atoms. New forces could also have a profound impact on the life cycle of stars. The process of nuclear fusion in the core of a star is a delicate balance between the inward pull of gravity and the outward push of the thermal pressure from the fusion reactions. A new force, if it could operate within the extreme conditions of a stellar core, could alter this balance. It could change the rate of fusion, leading to stars with different luminosities, different temperatures, and different lifespans. It could also influence the final, explosive death of a massive star in a supernova. The complex physics of a core collapse supernova is still not fully understood, and it is possible that a new short-range force plays a crucial role in re-energizing the stalled shockwave and driving the explosion. The fundamental constants of nature themselves might not be so constant in a universe with new forces. Many theories that propose new ultralight scalar fields predict that these fields could couple to the particles of the standard model, and as the value of the field evolves over cosmic time, it could cause the constants of nature, like the fine structure constant or the ratio of the proton to electron mass, to slowly change. The search for a temporal or spatial variation in these constants is a major focus of high-precision observational astronomy. A definitive detection of such a variation would be a revolutionary discovery, a sign that the laws of physics are not a fixed, static set of rules, but are part of the dynamic, evolving fabric of the cosmos itself. Finally, new forces could lead to the existence of entirely new, exotic, and stable macroscopic objects, in the same way that the strong nuclear force allows for the existence of atomic nuclei. A new confining dark force could allow for the existence of dark nuclei, or dark atoms. And on a much larger scale, some theories predict the existence of cueballs or solitons, stable, lump-like configurations of a new scalar field. That could be a form of dark matter or could have other observable astrophysical consequences. The universe is a vast and creative laboratory, and it is entirely possible that the four forces we know are just the tip of a much larger and much stranger cosmic iceberg. The search for new forces is a search for a more complete and more accurate picture of this hidden reality. The discovery of a new fundamental force would not just be a matter of adding a new column to the table of known interactions in our physics textbooks. It would be a moment of deep conceptual upheaval, a moment that would force us to fundamentally reevaluate and likely to revise our most successful and cherished theory of the subatomic world, the Standard Model of particle physics. The Standard Model is a beautiful and remarkably predictive theory, but it is also a strangely ad hoc and incomplete one. It is a house that is beautifully decorated and structurally sound, but whose architectural plans are a mystery. The discovery of a new force would be like finding a hidden blueprint, a clue that would reveal the deeper underlying principles upon which the house was built. For example, a new force could be the key to solving the hierarchy problem. The question of why the Higgs boson is so incredibly light compared to the natural Planck scale of gravity. The existence of a new force and its associated new particles at the TeV energy scale could provide a natural explanation for this lightness through mechanisms like supersymmetry or extra dimensions. A new force could also be the key to understanding the pattern of the particle masses themselves. The Standard Model has a strange three-generation structure for the quarks and the leptons, with each generation being a heavier, but otherwise identical, copy of the one before it. The masses of these particles span a huge range and seem to follow no discernible pattern. They are free parameters that we must simply measure and plug into the theory. A new flavor force that communicates between the different generations could be the key to explaining this mysterious family structure and the origin of the particle masses. A new force could also be the missing piece in the puzzle of grand unification. As we have seen, the strengths of the three forces of the Standard Model seem to almost, but not quite, meet at a single point at very high energies. The existence of new particles associated with a new force or with a framework like supersymmetry could change the way these force strengths evolve with energy, causing them to meet with perfect precision at a single grand unification point. This would be a powerful and beautiful sign that we are on the right track towards a deeper, unified understanding of nature. The discovery of a new force would also, almost certainly, come with the discovery of a new force-carrying boson. And the properties of this new particle, its mass, its spin, its couplings to the other particles would provide a wealth of information about the nature of the new interaction and the underlying symmetry group from which it arises. It would be a new window into the mathematical structure of the universe. The Standard Model is a theory that is, in many ways, a victim of its own success. It works so well that it has, for decades, provided very few clues about where to look for the new physics that we know must lie beyond it. The discovery of a new force would be the first definitive crack in this beautiful but ultimately incomplete edifice. It would be the thread that we could begin to pull on, a thread that could lead us to unravel the deeper and more profound tapestry of a true, unified theory of everything. The laws of thermodynamics, the great overarching principles that govern the flow of energy and the evolution of disorder in our universe, are so robust and so universally applicable that they are often considered to be the most fundamental laws of all. But even these seemingly unassailable laws could be challenged, or at least profoundly recontextualized, by the discovery of a new fundamental force, the first law of thermodynamics, the conservation of energy, states that the total energy of an isolated system is always constant. But what if our universe is not a truly isolated system? Many theories that propose new forces, particularly those with extra dimensions, envision our universe as a brane floating in a higher dimensional bulk. In this scenario, it is possible that energy could leak from our brane into the bulk, or from the bulk onto our brane. This would manifest in our universe as an apparent violation of energy conservation. A high-energy particle collision at the LHC, for example, could create a graviton that escapes into the extra dimensions, carrying energy with it. The signature of such an event would be missing energy in our detectors. The search for such missing energy events is a major focus of the LHC's research program, and a definitive observation would be a stunning confirmation of the existence of extra dimensions and a sign that the law of energy conservation only holds for the total higher dimensional system. The second law of thermodynamics, the law of increasing entropy, is what gives time its arrow. It is the law that says that the universe as a whole is moving towards a state of greater disorder, of heat death. But a new force could have a profound impact on this cosmic story. For example, some speculative models of dark energy propose that it is not a constant, but a dynamic field that is slowly decaying, releasing energy into the universe. This would be a constant source of negentropy, of new order, that could counteract the overall trend of increasing entropy. In a more radical scenario, a new force could be linked to the very origin of the low-entropy initial conditions of the universe, perhaps the process that gave rise to the Big Bang. Whether it was the decay of a false vacuum in an inflationary model or the collision of two branes in a cyclic one, was a process that was governed by a new entropy-reducing force, a force that reset the cosmic clock and created the highly ordered state from which our universe's arrow of time could begin. The connection between gravity and thermodynamics is another deep and mysterious area where a new force could play a role. The discovery that black holes have a temperature and an entropy. A discovery that was born from the work of Jacob Bekenstein and Stephen Hawking, is one of the most profound insights in all of theoretical physics. It suggests a deep, and as yet not fully understood, connection between the geometry of space-time, the laws of quantum mechanics, and the principles of thermodynamics. A new force could modify the properties of black holes, changing their entropy, their temperature, and their rate of evaporation. This would have a profound impact on our understanding of this deep holographic connection between gravity and information. The laws of thermodynamics are not just abstract, physical principles. They are the very framework that makes life and complexity possible. We are creatures of entropy, beings who maintain our own local state of high order by consuming energy and exporting disorder into our environment. The existence of a strong arrow of time, of a universe that is far from thermal equilibrium, is the ultimate precondition for our own existence. The discovery of a new force, one that could change the cosmic story of energy and entropy, would therefore be a discovery that would not just change our physics. It would change our understanding of our own deep and intimate connection to the thermodynamic unfolding of the cosmos. The discovery of a new fundamental force would not just be a revolution in science, it would be a revolution in philosophy. It would be a moment that would force us to confront, in a new and powerful way, our most basic and deeply held assumptions about the nature of reality, of knowledge, and of our own place in the cosmos. At its most fundamental level, it would be a profound lesson in epistemological humility. It would be a stark and undeniable reminder that our current scientific picture of the world, as successful and as powerful as it is not a final and complete description of reality. It is a provisional map, a work in progress, a single frame in a long and still unfolding movie of discovery. The existence of a force that has been operating in the universe for 14 billion years, a force that has been shaping the evolution of the cosmos and the very fabric of reality, and yet has remained completely hidden from us until now, should fill us with a deep sense of wonder and a deep sense of caution about the hubris of our own knowledge. A new force would also reignite the age-old philosophical debate about the nature of scientific truth. Does science progress in a linear, cumulative way, with each new discovery adding another, solid brick to the edifice of our knowledge, or does it progress through a series of paradigm shifts? As the philosopher of science Thomas Kuhn argued, where our entire worldview, our entire way of seeing and of understanding the world is periodically and radically overturned. The discovery of a new fundamental force would be a paradigm shift of the highest order. It would force us to not just add a new chapter to our textbooks, but to rewrite the entire book from the beginning. The implications for our understanding of causality could also be profound. Our classical, intuitive notion of causality is a local and linear one. Things are influenced by their immediate surroundings, and cause always precedes effect. But the quantum world, with its phenomena of entanglement and non-locality, has already challenged this simple picture. A new force, particularly one that is associated with extra dimensions or with a deeper quantum gravitational reality, could have even stranger causal properties. It could be a force that connects distant parts of the universe in a way that is not limited by the speed of light, or a force that is linked to the probabilistic and nonlinear nature of time itself. This would force us to adopt a much more holistic, more interconnected, and less mechanistic view of the universe. The discovery of a new force would also have a deep impact on the great existential questions that have always been at the heart of the human quest for meaning. It would, in a sense, make the universe a larger and more mysterious place. It would open up new possibilities for the nature of reality, for the existence of other worlds, of other dimensions, of other hidden aspects of the cosmos. This can be a source of both exhilaration and of a kind of cosmic vertigo. But it is a vertigo that is, in the end, a healthy one. It is the feeling that comes from standing at the edge of a great and newly discovered frontier. It is the feeling of a mind that is expanding to accommodate a larger and more wondrous reality. And finally, the discovery of a new force would have a profound impact on the dialogue between science and spirituality. It would be a powerful reminder that the universe is not a closed, fully understood, and disenchanted machine, but is an open, evolving, and deeply mysterious reality. It would be a discovery that could foster a renewed sense of awe, of reverence, and of a shared human participation in the ongoing, and perhaps infinite, unfolding of a cosmic mystery. The sheer scale of the universe, the vastness of the distances, and the immensity of the timescales is a concept that is almost impossible for the human mind to truly, intuitively grasp. Our brains evolved to navigate the mesoscopic world of our immediate terrestrial environment, a world of meters and of years. The language of cosmology is a language of numbers so large that they lose all their familiar meaning. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is about 93 billion light-years in diameter. A light-year, the distance that light travels in a single year, is about 6 trillion miles. This is a distance that is already far beyond our direct human experience. But the universe contains structures that are built on scales that are even more mind-boggling. Our own Milky Way galaxy, our home, is a swirling, spiral city of about 200 billion stars, and it is about 100,000 light-years across. To travel from one side of our galaxy to the other, even at the speed of light, would take 100,000 years. And our galaxy is not alone. It is part of a small, gravitationally bound cluster of about 50 galaxies called the local group. The local group, in turn, is just one small, outlying component of a much larger structure, the Virgo supercluster, a vast collection of thousands of galaxies that stretches across about 110 million light-years of space. And even this immense supercluster is just a single filament in an even grander cosmic structure. On the very largest scales, the universe is organized into a cosmic web, a vast, intricate, and beautiful network of galaxy clusters and superclusters, arranged in long, thin filaments and broad, flat walls, all surrounding immense, nearly empty cosmic voids. The Laniakea supercluster, the galactic superstructure that our own Milky Way calls home, is a sprawling, filamentary metropolis of about 100,000 galaxies, and it is over 520 million light-years in diameter. And as we have seen, there are even larger structures, like the recently discovered Hercules Corona Borealis Great Wall, a concentration of galaxies that seems to stretch for a staggering 10 billion light-years, a structure so large that it challenges our most basic cosmological principle of homogeneity. The history of the universe is a story that is played out on an equally unimaginable timescale. The universe is about 13.8 billion years old. If we were to compress this entire cosmic history into a single calendar year, with the Big Bang happening at the first second of January 1st, then our own Milky Way galaxy would form sometime in May. Our solar system would not appear until early September. The first, simple, single-celled life on Earth would emerge by the end of September. The great age of the dinosaurs would be a brief period in the last week of December, and the entire recorded history of human civilization, from the first cities to the present day, would take up just the last 10 seconds of New Year's Eve. Our own individual human lifespan, in this cosmic calendar, is less than the blink of an eye. This vastness of space and time is not just a source of intellectual wonder, it is a profound, and perhaps necessary, source of existential perspective. It is a powerful antidote to our own human-centered arrogance. It is a reminder that our own lives, our own problems, our own conflicts are, in the grand scheme of things, incredibly small and fleeting, but it is also a source of deep and perhaps paradoxical meaning. The fact that in this vast and largely empty cosmos, on a small, insignificant planet orbiting a very average star, a form of matter has arisen that is capable of looking back at the universe, of understanding its scale, of deciphering its laws, of appreciating its beauty, is perhaps the most wonderful and astonishing fact of all. We are the universe's way of knowing itself. We are the part of the cosmos that has woken up. And our tiny, fleeting, and precious moment of conscious existence is imbued with a significance that is, in its own way, as vast as the cosmos itself. The existence of new fundamental forces would not just add a new layer of complexity to our understanding of the universe. It could fundamentally reshape the very process of cosmic structure formation, leading to a universe with a different architecture, a different history, and a different ultimate fate. The story of structure formation in our standard four-force model is a relatively simple and elegant one. It is a story that is governed primarily by the gentle, patient, and relentless pull of gravity. In the early universe, there were tiny quantum fluctuations in the density of matter. The regions that were slightly denser than average had a slightly stronger gravitational pull, and they began to attract the matter from the surrounding, less dense regions. This is a process of gravitational instability, a classic rich-get-richer scheme. Over billions of years, this process has amplified the initial tiny density fluctuations into the vast cosmic web of galaxies, clusters, and superclusters that we see today. The invisible dark matter plays a crucial role in this story, because dark matter does not interact with light. It was able to start clumping together much earlier than the normal. Baryonic matter, forming the deep gravitational wells or halos into which the normal matter would later fall, eventually cooling and condensing to form the stars and the galaxies. But what if there was another force at play in this cosmic drama? A new long-range force could have a profound impact on this process. A new attractive force, for example, could have accelerated the process of structure formation, leading to the formation of galaxies and clusters much earlier in cosmic history. This could be a potential solution to the puzzle presented by the James Webb Space Telescope, which seems to be finding galaxies that are surprisingly mature and well-formed at very early times. A new repulsive force, on the other hand, could have hindered the process of gravitational collapse, leading to a universe with a less clumpy, more diffuse structure. This could help to solve some of the small-scale challenges of the standard cold dark matter model, like the core cusp problem. The fact that the centers of some galaxies seem to be less dense than our simplest models predict. A new force that only acts on dark matter, or would be particularly intriguing. It could cause the dark matter to behave in a much more complex way, allowing it to cool down, to dissipate energy, and to form its own dark structures, like dark matter disks or even dark atoms. The universe could be home to a whole, hidden, and parallel world of dark matter structures, a world that we can only perceive through its subtle, gravitational influence. The evolution of the cosmic voids, the vast, empty regions of the cosmic web, would also be affected by a new force. A repulsive force, like dark energy, is what drives the growth of these voids, pushing the matter out of them and into the surrounding filaments and walls. A new force could change the dynamics of this process, leading to voids with different sizes, different shapes, and a different degree of emptiness. The large-scale structure of the universe is a delicate and beautiful tapestry, woven from the threads of the initial quantum fluctuations and shaped by the interplay of cosmic expansion, of gravity, and of the other fundamental forces. The discovery of a new force would be like discovering a new and previously unknown thread in this tapestry. It would not just add a new detail to the picture, it would change the entire pattern, and it would give us a new and more powerful tool for understanding the deep, and still mysterious, connection between the quantum world of the very small and the cosmological world of the very large. The connection that is at the heart of the entire, beautiful, and ongoing story of our cosmic home. The evolution of our universe, from the fiery simplicity of the Big Bang to the cool, complex, and structured cosmos we see today, is a story of a progressive breaking of symmetry. In the very first moments of the universe, at the incredibly high energies of the Planck era, it is thought that all the fundamental forces of nature were unified into a single primordial superforce, governed by a single, large, and highly symmetric mathematical group. The universe, in this state, was a perfect, undifferentiated, and featureless whole. But as the universe expanded and cooled, it underwent a series of phase transitions, similar to the way that water vapor, as it cools, condenses into liquid water and then freezes into solid ice. At each of these phase transitions, a part of the primordial symmetry was spontaneously broken, and a new and more complex structure emerged. The first of these phase transitions may have been the one that separated gravity from the other, grand unified force. The next one, at the gut energy scale, would have been the one that broke the grand unified symmetry, causing the strong nuclear force to freeze out as a separate interaction. And the final phase transition, at the electroweak scale, would have been the one that broke the electroweak symmetry, separating the electromagnetic and weak nuclear forces and giving the fundamental particles their mass through the Higgs mechanism. The discovery of a new fundamental force would be a profound new piece of this historical puzzle. It would imply the existence of a new and previously unknown symmetry group in the fundamental laws of nature, a symmetry that is broken at some, as yet unknown, energy scale. The properties of this new force, its strength, its range, its couplings to the other particles would give us a clue about the nature of this new symmetry and about the energy scale at which it was broken. A new force could also have a profound impact on the evolution of the early universe. The phase transitions that break these fundamental symmetries are not always smooth. Gentle processes. They can be violent, dynamic events, and they can leave behind topological defects. Stable. Remnant structures of the old, more symmetric vacuum state that can persist to the present day. These defects, as we have seen, can be one-dimensional cosmic strings, two-dimensional domain walls, or zero-dimensional monopoles. The existence of a new force, associated with a new broken symmetry, would open up the possibility of a whole new class of these exotic astrophysical objects. The detailed, observational search for these topological defects is a powerful, if indirect, way to probe the physics of the very early universe and to search for the signatures of new, broken symmetries. The evolution of the universe is a story of a progressive unfolding of complexity, a story of how, from a state of perfect and, in a sense, sterile symmetry, all the rich and diverse structures of our world have gradually emerged. And the fundamental forces of nature are the rules that have governed this process of cosmic symmetry breaking. The discovery of a new force would not just be about adding a new rule to the game. It would be about discovering a new and deeper layer of the game itself. A layer that would give us a new and more profound understanding of the beautiful and still mysterious connection between the timeless, mathematical world of symmetry and the dynamic, evolving, and beautifully asymmetric world of our own lived experience. The existence of a new fundamental force could have a profound and transformative impact on our understanding of black holes, those enigmatic and extreme objects that represent the ultimate victory of gravity over all other forces. In our current four-force picture, a black hole is a remarkably simple object, according to the no-hair theorem of general relativity. A stable, astrophysical black hole is completely characterized by just three properties: its mass, its spin, and its electric charge. All the other detailed information about the matter that collapsed to form the black hole is seemingly lost forever behind the event horizon. But a new force could change this simple picture in a number of dramatic ways. If the new force is a long-range force, mediated by a new light and perhaps massless boson, then a black hole could also have a new kind of hair. It could have a charge associated with this new force, and it would be surrounded by a new long-range field. This would mean that a black hole is not as simple as we thought, and it would provide a new and potentially observable way to probe the physics beyond the standard model. We could, in principle, detect the effects of this new long-range field on the orbits of stars and other matter around the black hole. A new force could also have a dramatic impact on the process of Hawking radiation, the quantum mechanical process by which black holes are thought to slowly evaporate. The rate of Hawking radiation and the spectrum of the particles it produces depends on the number and the properties of all the fundamental particles that exist in nature. If there are new particles associated with a new force that are light enough to be produced in the Hawking process, then a black hole would evaporate faster than our standard calculations predict. The detailed thermal spectrum of the Hawking radiation would also be changed. In the very final moments of a black hole's evaporation, when its temperature becomes incredibly high, it would radiate a shower of all the fundamental particles of nature, including the particles of any new, hidden sectors. The ability to detect the final, explosive burst of a small, evaporating primordial black hole would be a powerful and unique window into the full spectrum of fundamental particles and forces. A new force could also play a role in resolving the deep, conceptual paradoxes of black hole physics, like the information paradox and the nature of the singularity. Some theories that propose a new, short-range, repulsive force, for example, suggest that this force could become dominant at the incredibly high densities found inside a black hole, preventing the formation of a true, infinite singularity and replacing it with a new, exotic, and ultra-dense site of matter. The interplay between gravity and a new force could also be the key to understanding the deep, holographic connection between the geometry of space-time and the quantum information that is stored on the event horizon. The universe of black holes is a universe of extremes, a place where the laws of physics are pushed to their absolute limits. And it is in these extreme, and still mysterious, environments that the subtle effects of a new, and as yet undiscovered, force of nature may be most clearly and powerfully revealed. The behavior of the fundamental forces in the extreme and exotic environments of the cosmos is a powerful and fascinating probe of the underlying laws of nature. And nowhere are these environments more extreme than in the vicinity of a neutron star. A neutron star is the incredibly dense, city-sized remnant of a massive star that has exploded in a supernova. It is, in essence, a giant atomic nucleus, with a mass of up to twice that of our Sun, compressed into a sphere with a radius of just 10 kilometers. The density of matter in the core of a neutron star is so high that normal atoms cannot exist. The immense pressure has crushed the electrons and the protons together to form a sea of tightly packed neutrons, a state of matter known as neutronium. In this extreme environment, the four fundamental forces of nature behave in ways that are very different from our everyday experience. Gravity, of course, is incredibly strong. The gravitational field at the surface of a neutron star is hundreds of billions of times stronger than that on Earth. This intense gravity warps the fabric of space-time around the star so dramatically that light is visibly bent, and time itself is slowed down. Electromagnetism also plays a crucial, and often dramatic, role. Neutron stars are born spinning incredibly rapidly, and they have some of the strongest magnetic fields in the entire universe. A magnetar is a particular type of neutron star with a magnetic field that is 1,000 times stronger than that of a normal neutron star. A field so powerful that it can buckle the star's solid crust, creating a starquake and releasing a vast, and often destructive, burst of gamma rays and X-rays. In this ultra-strong magnetic field, the very vacuum of space is thought to become polarized, a bizarre quantum effect that should affect the way that light propagates. But it is the two nuclear forces, the strong and the weak, that truly dominate the inner world of a neutron star. The strong nuclear force is what provides the primary, outward pressure that supports the star against the immense, inward crush of gravity. The balance between these two titanic forces is what determines the stability and the ultimate fate of the star. If the star is too massive, even the incredible repulsive pressure of the strong force will not be enough to halt the gravitational collapse, and the neutron star will continue to collapse to form a black hole. The weak nuclear force is also crucial. It is the force that governs the processes of neutron decay and electron capture, processes that determine the detailed composition and the thermal evolution of the star's core. The interior of a neutron star is a deep and mysterious place, a realm where our understanding of nuclear physics is pushed to its absolute limits. We do not know for sure what the state of matter is in the very center of a neutron star, It may be a simple sea of neutrons, or at these incredible densities, the neutrons themselves may break down into a new and even more exotic state of matter, a quark-gluon plasma. The same state that is thought to have existed in the very first moments of the universe's existence. A neutron star is a cosmic laboratory, a place where we can study the behavior of matter and the interplay of the fundamental forces under conditions that we can never hope to replicate on Earth. And it is a place where the subtle effects of a new, and as yet undiscovered, fifth force could be amplified and made manifest. A new force could change the equation of state of the dense nuclear matter, changing the maximum possible mass of a neutron star. It could affect the star's cooling rate or the properties of its magnetic field. By precisely measuring the properties of neutron stars, their masses, their radii, their spin rates, their temperatures, and by comparing these observations with the predictions of our theoretical models, we can place powerful constraints on a wide range of new physics. The study of these extreme and beautiful objects is a powerful and complementary approach in our ongoing, multifaceted quest to discover the full, and perhaps still hidden, set of rules that govern our universe. The quest to understand the behavior of the fundamental forces in the very first moments of the universe's existence is a journey into a realm of almost unimaginable energy, density, and temperature. It is a journey that takes us back to a time before atoms, before nuclei, before even protons and neutrons, to a time when the universe was a hot, dense, and rapidly expanding soup of fundamental particles and forces. To theorize about this primordial era, to build a coherent and predictive model of the Big Bang, is one of the greatest and most profound challenges in all of science. Our primary tools in this endeavor are our two great theoretical frameworks, Einstein's general theory of relativity, which describes the dynamics of the expanding space-time, and the standard model of particle physics, which describes the behavior of the matter and the forces within it. By combining these two theories, we can create a powerful and remarkably successful standard model of cosmology, a model that can trace the evolution of the universe from about 1 microsecond after the Big Bang to the present day. This model successfully explains the expansion of the universe, the existence and the detailed properties of the cosmic microwave background, the primordial abundances of the light elements, and the formation of the large-scale structure of the cosmos. But the standard model is incomplete. It does not explain the origin of the universe itself, the nature of dark matter and dark energy, or the reason for the matter-antimatter asymmetry. And at the very earliest times, in the first infinitesimal fraction of a second, at the incredible energies of the Planck era, our current theories break down completely. This is the realm of quantum gravity, the realm where a new unified theory is needed. To explore these pre-standard model epochs, to try and build a theory of the very beginning, physicists have developed a number of powerful and often speculative theoretical tools. Cosmic inflation, as we have seen, is one of the most important of these. It is a theory that provides a dynamical explanation for the initial conditions of the hot Big Bang, and it makes specific, testable predictions about the properties of the primordial density fluctuations. String theory is another. It is a candidate theory of everything that has the potential to describe the physics of the Planck era and to provide a consistent quantum mechanical description of the universe's origin. Another crucial tool is the use of large-scale computer simulations. By programming the fundamental laws of physics into a powerful supercomputer, we can create a virtual universe in a box. We can set the initial conditions to match those inferred from the cosmic microwave background, and then we can let the simulation evolve for 14 billion years of virtual time, watching as the tiny initial density fluctuations grow under the influence of gravity and the other forces into a complex cosmic web of galaxies and clusters. These simulations are an essential bridge between our theories and our observations. They allow us to test our cosmological models in a detailed and quantitative way, to see if they can reproduce the complex statistical properties of the universe we actually observe. The behavior of the forces during the Big Bang is a story of a progressive unfolding of complexity from a state of primordial simplicity and symmetry. It is a story that is written in the language of theoretical physics, a story that we are slowly and patiently learning to read. And it is a story whose first and most mysterious chapter, the chapter that describes the very moment of creation itself, is still waiting for a final and complete theory to be written. The societal and technological impact of our long human journey of space exploration has been profound, far-reaching, and often unexpected. It is a journey that has not just expanded our knowledge of the cosmos, it has also transformed our world, our technology, our culture, and our very sense of what it means to be human. The most obvious and direct impact has been in the realm of technology. The intense and unforgiving demands of spaceflight have been a powerful driver of innovation in a host of different fields. The need for lightweight, robust, and reliable electronics for our spacecraft led directly to the development of the integrated circuit, the microchip that is now at the heart of our computers, our smartphones, and our entire digital world. The need for new, high-strength, lightweight materials for our rockets and our satellites has led to the development of new metal alloys, of composites, of ceramics, that are now used in everything from airplanes and cars to medical implants and sporting goods. The need to communicate with our robotic emissaries across the vast distances of the solar system has spurred a revolution in telecommunications, leading to the development of the satellite communication technologies that now connect our global village. The need to power our spacecraft in the dark, cold vacuum of space has led to the development of highly efficient solar cells and of long-lived, reliable nuclear power sources. And the need to keep our astronauts alive and healthy in the closed-loop environment of a spacecraft has led to breakthroughs in a host of different fields, from water purification and air recycling to medical monitoring and telemedicine. But the impact of space exploration goes far beyond these practical technological spin-offs. It has also had a profound and transformative impact on our culture and on our collective human consciousness. The space race of the 1960s, for all its Cold War origins, was a powerful and unifying force. It was a grand human adventure that captured the imagination of the entire world and inspired a generation to pursue careers in science, in technology, in engineering, and in mathematics. The image of the Earth as seen from space, the famous blue marble photograph taken by the crew of Apollo 17, has become one of the most iconic and influential images in all of human history. It is an image that has no borders, no divisions, no signs of the petty, human conflicts that have so often defined our history. It is an image of a single, beautiful, fragile, and interconnected world, a world that we all share, and a world that we all have a responsibility to protect. This overview effect, the profound cognitive shift in awareness that has been reported by so many astronauts, is perhaps the most important and most hopeful. Societal impact of space exploration. It is a perspective that can foster a sense of global unity, of environmental stewardship, and of a shared human destiny. And space exploration continues to be a powerful engine of inspiration and of education. The images from the Hubble Space Telescope, the live feeds from the International Space Station, the daily updates from the rovers on Mars, these are not just scientific data. They are a constant and beautiful reminder of the wonder, the beauty, and the vastness of the universe we inhabit. They are a source of inspiration for a new generation of explorers, of scientists, of dreamers. And they are a powerful antidote to the small-mindedness, the tribalism, and the short-term thinking that so often seem to dominate our world. The journey into space is a journey that has given us not just new technologies, but also a new perspective. And it is this new perspective, This new cosmic consciousness that may, in the end, be its most valuable and enduring gift to humanity. The discovery of a new, fundamental force of nature would not just be a matter of academic interest. It would be a discovery with the potential to unleash a new wave of transformative technologies. Technologies that could reshape our world in ways that we can currently only begin to imagine. The history of science is a testament to this powerful connection between fundamental discovery and technological revolution. The discovery of the laws of electromagnetism in the 19th century was, at the time, a purely intellectual pursuit, a quest to understand the nature of electricity, of magnetism, and of light. But it was a quest that would, in the span of just a few decades, lead directly to the invention of the electric motor, the generator, the radio, the television, and the entire technological infrastructure of our modern, electrified, and interconnected world. The discovery of the laws of quantum mechanics in the early 20th century was an even more profound and seemingly more abstract revolution, but it was a revolution that would lead directly to the invention of the transistor, the laser, the computer, and the entire digital age in which we are now living. What new technologies might a new force enable? The answer, of course, depends on the specific properties of the force, its strength, its range, its couplings to the other particles. But we can allow ourselves to speculate. If the new force is a long-range force, it could lead to new forms of communication, of energy transmission, or even of propulsion. If it is a short-range force, it could lead to new ways of manipulating matter at the atomic and nuclear level, with potential applications in material science, in medicine, and in energy production. If the new force is a dark force that communicates between our world and the world of dark matter, it could, in the far future, give us a way to see and to interact with the invisible, dark sector of the universe. This could lead to new forms of imaging, of sensing, and perhaps even of a new, dark technology. The connection between a new force and the quantum world is particularly intriguing. A new force could be the key to building a large-scale, fault-tolerant quantum computer. The primary challenge in quantum computing is decoherence, the process by which a quantum system loses its delicate, superpositional nature through its interaction with the environment. A new force could provide a new way to control and to shield our quantum bits, or qubits, from this environmental noise, allowing us to build much more powerful and more reliable quantum computers. And a quantum computer, in turn, could be a powerful tool for understanding the properties of the new force, a beautiful positive feedback loop between fundamental discovery and technological innovation in the realm of energy. A new force could open up completely new possibilities. Our current nuclear energy technologies, both fission and fusion, are based on our understanding of the strong and weak nuclear forces. A new force, with its own unique properties, could lead to new, and perhaps even more efficient, ways of releasing the immense energy that is stored in the heart of the atom. The journey from a fundamental discovery in physics to a transformative, world-changing technology is often a long, winding, and unpredictable one. It can take decades, or even centuries, and it requires a sustained and patient investment in basic, curiosity-driven research. The kind of research that is not aimed at a specific, short-term application, but is driven by the simple and powerful desire to understand the world at its deepest level. But it is a journey that is, in the end, one of the primary engines of human progress. And the discovery of a new, fundamental force of nature would be a moment that would not just ignite a new era of scientific discovery, but would also, almost certainly, plant the seeds for a new and currently unimaginable technological future. The future of our exploration of the cosmos, the missions that will be launched in the coming decades and centuries, will be shaped by the powerful and synergistic interplay of our evolving scientific questions and our ever-advancing technological capabilities. The questions we ask of the universe are becoming more profound, more ambitious, and more focused. And the tools we are building to answer these questions are becoming more powerful, more sensitive, and more intelligent. In the near term, in the coming decade, we will see a new wave of flagship missions that will build on the legacy of Hubble and the other great observatories. The James Webb Space Telescope is already revolutionizing our view of the infrared universe, and it will be joined by the Nancy Grace Roman Space Telescope, a wide-field survey telescope that will map the distribution of dark matter and dark energy with unprecedented precision, and that will use its coronagraph to directly image large, Jupiter-like planets around nearby stars. On the ground, a new generation of giant 30-meter class optical telescopes will provide a powerful synergy with these space-based observatories, allowing for the detailed, high-resolution follow-up of the most interesting objects they discover. The search for life beyond Earth will move from a process of simply detecting exoplanets to a process of characterizing their atmospheres. The techniques of transit spectroscopy, which Webb is pioneering, will be refined and scaled up, with the ultimate goal of building a future. Large, space-based telescope that is specifically designed to search for the chemical biosignatures of life in the atmospheres of dozens of nearby, Earth-like worlds. This would be a mission of profound, and perhaps civilization-changing, significance. The exploration of our own solar system will also enter a new and exciting phase. We will return to the moon, not just for brief, Apollo-style visits, but to stay. The Artemis program, a new international collaboration, will establish a permanent human research outpost on the lunar surface, a base camp that will serve as a testbed for the technologies and the operational strategies that we will need for the much longer and more challenging journey to Mars. The robotic exploration of the outer solar system will continue, with missions to the ice giants, Uranus and Neptune, and a new focus on the ocean worlds of Jupiter and Saturn, a future mission to Enceladus, for example, could fly through the plumes of water that are erupting from its south pole and sample them directly, searching for the organic molecules and the other chemical signs of a potential subsurface biosphere. Looking further into the future, the development of new, advanced propulsion technologies, like nuclear thermal and, eventually, nuclear fusion, will be the key to unlocking a new era of human exploration. These technologies will make a human mission to Mars a routine and sustainable enterprise, and they will open up the entire solar system to a new level of rapid and intensive exploration. And on the very longest timescales, on the timescale of centuries and millennia, the dream of interstellar travel may one day move from the realm of science fiction to the realm of engineering. The development of a fusion-powered world ship or a beam-powered relativistic probe would be a project of almost unimaginable complexity and scale. But it is a project that is not forbidden by the known laws of physics. It is a project that is, in principle, possible. The future of space exploration is a future of ever-expanding horizons, a future where each new discovery, each new technology opens up a new set of questions, a new set of possibilities, a new frontier to explore. It is a journey that is driven by our deepest and most noble human impulse, the desire to understand, to explore, and to reach for the stars. And it is a journey that is, in the end, not just about the cosmos, but about ourselves, about our own limitless potential for growth, for discovery, and for a future that is as vast and as wonderful as the universe itself. The search for new fundamental forces is not just a quest to complete our inventory of the cosmos. It is a quest that could provide the key to a deeper, more unified, and more elegant understanding of the laws of nature. It is a quest that is driven by the deep and almost aesthetic belief that the universe, at its most fundamental level, is simple and beautiful. And one of the most powerful and beautiful ideas in this quest is the idea of symmetry. Symmetry is a concept that we are all intuitively familiar with. A sphere is symmetric because it looks the same no matter how you rotate it. A snowflake is symmetric because it has a beautiful six-fold rotational symmetry. In physics, a symmetry is a transformation that you can perform on a system that leaves its fundamental properties, its laws of physics, unchanged. And a profound and beautiful theorem, Noether's theorem, tells us that for every continuous symmetry in nature, there is a corresponding conserved quantity. The fact that the laws of physics are the same today as they were yesterday. A symmetry in time translation leads to the conservation of energy. The fact that the laws of physics are the same here as they are on the other side of the galaxy. A symmetry in space translation leads to the conservation of momentum. The symmetries of nature are not just a matter of aesthetic beauty. They are the deep, underlying source of the conservation laws that govern our universe. The forces of the Standard Model are also based on a kind of symmetry, a more abstract, internal symmetry called a gauge symmetry. The theory of electromagnetism, for example, is based on a simple U-gauge symmetry, say, and the requirement that the laws of physics be invariant under this symmetry. Transformation naturally and inevitably leads to the existence of the electromagnetic force and its force-carrying particle, the photon. The electroweak theory is based on a larger SU-XU symmetry group, and the strong nuclear force is based on an even larger SU symmetry group. The quest for a grand unified theory is, in essence, a search for a single, even larger symmetry group that contains all three of these, a group like SU or SO. The discovery of a new fundamental force would be a direct and powerful clue about the existence of a new and previously unknown gauge symmetry in the laws of nature. By studying the properties of this new force, we could begin to deduce the mathematical structure of this new symmetry group, and to understand how it fits into the larger, and perhaps unified, picture of all the forces. The breaking of these symmetries is as important as the symmetries themselves. As we have seen, the universe, as it cooled after the Big Bang, is thought to have undergone a series of spontaneous symmetry-breaking phase transitions. The Higgs mechanism is the most famous example of this. At high energies, the universe was in a symmetric, electroweak state. But as the universe cooled, the Higgs field condensed into a particular vacuum state, a process that broke the electroweak symmetry and gave mass to the W and Z bosons, while leaving the photon massless. This process of symmetry breaking is what gives rise to the rich and complex structure of the world we see. The search for a new force is, in this sense, a search for the history of cosmic symmetry breaking. It is a form of cosmic archaeology, a quest to uncover the fossilized remnants of the more symmetric and more unified state of the very early universe. The symmetries of nature are the deep and often hidden source of the order, the beauty and the mathematical elegance of the physical world, and the quest to discover new forces and the new symmetries from which they arise is a quest to read the very mind of God, to understand the single, beautiful, and unified thought that is the source of our entire, vast, and wonderful cosmos. The public's fascination with the mysteries of the universe is a deep and often untapped well of curiosity and wonder. But the language of modern physics, with its abstract mathematics and its counterintuitive concepts, can often seem like an impenetrable barrier, a secret code that is accessible only to a small, initiated priesthood of professional scientists. Bridging this gap, translating the profound and beautiful ideas of fundamental physics into a language that is accessible, engaging, and meaningful to a wider audience is one of the most important and challenging tasks for the scientific community today. One of the most effective strategies for doing this is to connect the abstract concepts of physics to the concrete, lived experiences of our everyday lives. The laws of thermodynamics, for example, can be explained not just with equations, but with the familiar experience of a cooling cup of coffee. The curvature of space-time can be visualized with the analogy of a bowling ball on a rubber sheet, and the strange quantum world of superposition and uncertainty can be made more tangible, if not fully intuitive, through its powerful and resonant metaphors with the nature of our own consciousness. With the experience of sleep and of dreams, storytelling is another powerful tool. The history of science is not a dry, linear progression of facts and theories. It is a rich and dramatic human story. A story of brilliant and often flawed individuals, of intense rivalries and deep collaborations, of moments of sudden, breathtaking insight, and of long, patient years of hard, meticulous work. By telling these stories, by putting a human face on the abstract enterprise of science, we can make the process of discovery more relatable, more inspiring, and more deeply human. The visual medium, in all its forms, is also a crucial part of this effort. The breathtaking images from the Hubble Space Telescope have done more to capture the public's imagination and to inspire a sense of cosmic awe than 1,000 scientific papers. The beautiful and intuitive animations that can be created with modern computer graphics can make the invisible world of quantum fields or the vast four-dimensional landscape of space-time visible and almost tangible. The rise of new media platforms, from YouTube and podcasts to social media and virtual reality, has created a new and powerful ecosystem for science communication. These platforms allow scientists to speak directly to the public, to share their passion and their excitement, and to engage in a real and often lively two-way dialogue. This is a powerful way to break down the traditional barriers between the experts and the laity, and to foster a more democratic and participatory culture of science. And finally, there is the crucial role of hands-on, experiential learning, science festivals, museum exhibits, citizen science projects. These are all ways to give people a direct, personal experience of the process of scientific discovery. To look through a telescope and to see the rings of Saturn for yourself. To participate in the search for new pulsars by analyzing radio astronomy data on your own computer. These are experiences that can ignite a lifelong passion for science and for the universe. The quest to understand the fundamental laws of nature is not a journey for a small, elite group of specialists. It is a shared human adventure. An adventure that speaks to our deepest and most ancient questions about who we are, where we came from, and what our place is in the grand and cosmic scheme of things. And by finding new and more creative ways to share the stories, the beauty, and the wonder of this journey, we can invite all of humanity to participate in this great and ongoing conversation with the cosmos. Galaxies, those magnificent islands of stars, dust, and dark matter, have held a profound and enduring grip on the human imagination for centuries. From the faint, milky smudge of our own galaxy arching across a dark night sky to the stunning, detailed portraits of distant spirals captured by our most powerful telescopes. They are the grand architectural pillars of the cosmos, At first glance, they might seem like isolated, self-contained entities, marbles of light scattered across the vast, dark expanse of space. We see the elegant, pinwheeling arms of spiral galaxies, the serene, golden glow of elliptical giants, and the chaotic, misshapen forms of irregulars, hinting at a history of violent, cosmic collisions. But this picture of isolation is a profound illusion. These galactic structures are not solitary islands. They are the luminous nodes in a vast, interconnected tapestry that weaves the entire universe together. This is the cosmic web, an immense and intricate network of filaments stretching for billions of light-years across the cosmos, a celestial superhighway of matter and energy. At the intersections of these filaments, we find the great galaxy clusters, the bustling metropolises of the universe. The filaments themselves are the cosmic byways, trails of galaxies and intergalactic gas that connect these clusters, while the vast, seemingly empty voids in between are the silent, dark countrysides. The very existence of this cosmic web raises a host of deep and fundamental questions. Why do galaxies cluster along these specific, filamentary structures? What invisible forces guide the flow of matter across the immense voids? The answers, we are learning, lie beyond the realm of the visible. They lead us into the domain of the unseen, the mysterious, and the profoundly powerful. The grand architectural scaffolding of the cosmic web is not built from the stars and gas we can see. It is shaped by a mysterious and invisible substance known as dark matter. This enigmatic entity, which we cannot see or touch, which does not emit, absorb, or reflect any form of light, is the silent, gravitational majority of the universe, outweighing all the normal, baryonic matter by a factor of more than 5 to 1. It is the unseen hand that has guided the formation of every galaxy, every cluster, every filament in the cosmos. But dark matter is not the only invisible force at play. Looming at the heart of almost every massive galaxy is a supermassive black hole, a region of space-time where gravity is so intense that nothing, not even light, can escape. These are not passive, cosmic drains, silently swallowing matter. They are dynamic and powerful engines, their immense gravitational pull dictating the orbits of billions of stars, and their ferocious, high-energy outbursts of radiation and particles regulating the very process of star formation within their host galaxies. They are a profound paradox, a point of ultimate destruction that is also a key agent of cosmic order and creation. And the cosmic drama does not end with these internal forces. Galaxies are social creatures. They are constantly interacting, their immense gravitational fields reaching out across millions of light years to pull on their neighbors. These interactions can be subtle, a gentle tidal stripping of a small satellite galaxy by its massive host, or they can be cataclysmic, a head-on collision between two spiral galaxies of equal size. These major mergers are some of the most spectacular and transformative events in the universe. Cosmic dances of creation and destruction that unfold over hundreds of millions of years. As the two galaxies collide, their vast clouds of interstellar gas are compressed, triggering a furious burst of star formation. A starburst that can briefly outshine all the other stars in the galaxy combined. The elegant spiral structures are torn apart, their stars flung into long tidal tails, and eventually the two galaxies will merge into a single, larger, and often elliptical galaxy. These collisions are a primary driver of galactic evolution, shaping the size, the structure, and the destiny of the galaxies we see today. But even as we begin to understand this intricate dance of dark matter, black holes, and galactic collisions, we are confronted with an even deeper and more pervasive mystery, the existence of dark energy. This is a strange, repulsive force, a property of space itself. that is causing the expansion of the entire universe to accelerate. While its existence is now well established by our observations, its fundamental nature remains a complete enigma. Is it a constant, unchanging property of the vacuum, or is it a dynamic entity whose strength changes over cosmic time? The answer to this question will determine the ultimate fate of our universe and the ultimate fate of the very galaxies we are trying to understand. And then there is the most profound question of all, the question that underlies all of our cosmological inquiries. Why does the universe exist in this particular form? Could it have been different? Are there other parallel realities? Other universes where the laws of physics are different, where galaxies formed in a completely different way? Or perhaps where they never formed at all? These are the grand, open-ended puzzles that fuel the relentless, passionate curiosity of astronomers, physicists, and cosmologists. Every star, every orbit, every galactic spin is a thread in the cosmic tapestry, a clue in a detective story that is billions of years in the making. Today, we begin to pull on some of these threads, to peel back the cosmic veil, and to explore the forces, the entities, and the enigmas that have shaped the magnificent galactic islands we call home. The story of galaxy formation begins not with stars or gas, but in the fiery, primordial crucible of the Big Bang itself. This is the moment, some 13.8 billion years ago, when not just matter and energy, but space and time themselves exploded into being. The popular image of the Big Bang as an explosion in space is a misleading one. It was an expansion of space, an event that happened everywhere at once, in the first infinitesimal fractions of a second. The universe was an unimaginably hot and dense singularity, a point of infinite temperature and density where our current laws of physics break down. This was followed by a period of astonishing, hyper-accelerated expansion known as cosmic inflation, a process that stretched the nascent universe from a subatomic size to something larger than a grapefruit in a time far shorter than the blink of an eye. As this inflationary period ended, its immense energy was converted into a hot, dense soup of fundamental particles. This was the true beginning of the hot Big Bang phase. At these extreme temperatures, well into the trillions of degrees, the familiar particles of our world could not exist. The universe was a quark-gluon plasma, a chaotic, seething sea of the most fundamental building blocks of matter quarks and the gluons that bind them along with photons, electrons, and other elementary particles. As the universe continued to expand and cool, it passed through a series of critical phase transitions. After about 1 microsecond, the temperature had dropped enough for the quarks and gluons to freeze out, combining in groups of 3 to form the first protons and neutrons, the building blocks of atomic nuclei. This was a pivotal moment, but it was also a moment of profound and enduring mystery. The laws of physics, as we understand them, are almost perfectly symmetric with respect to matter and antimatter. For every type of particle, there should be an antiparticle with the same mass but opposite charge. In the intense heat of the early universe, particles and antiparticles should have been created in equal amounts. And when a particle meets its antiparticle, they annihilate each other in a burst of pure energy. This means that as the universe cooled, almost all the matter and antimatter should have annihilated, leaving behind a universe filled with nothing but a diffuse bath of radiation. But this is not what we see. We live in a universe that is made almost entirely of matter. For every billion antiparticles in the early universe, there must have been 1,000,000,001 particles of matter. This tiny 1 in a billion imbalance. This slight preference of the universe for matter over antimatter is the reason that we exist. The process that created this imbalance is known as baryogenesis, and its precise mechanism remains one of the great unsolved puzzles in modern physics. It is a mystery that is deeply connected to the fundamental symmetries of nature, and its solution will likely require a new physics beyond our current standard model. As the universe continued its journey of cooling and expansion, it entered the next crucial phase of its early evolution, Big Bang nucleosynthesis. Between about 1 and 3 minutes after the Big Bang, the temperature had dropped to a mere billion degrees, cool enough for the protons and neutrons to begin to fuse together. Forming the nuclei of the first light elements, the universe became a primordial nuclear reactor. Protons and neutrons combined to form deuterium, which then fused to form helium-4, along with trace amounts of helium-3, lithium, and beryllium. This process was incredibly efficient, but also very short-lived. After about 20 minutes, the universe had expanded and cooled to the point where nuclear fusion was no longer possible. The result was a universe whose baryonic matter was composed of about 75% hydrogen nuclei, 25% helium nuclei, and a tiny fraction of lithium. The precise predictions of Big Bang nucleosynthesis for the abundances of these light elements are one of the great triumphs of the Big Bang model, matching our observational measurements with stunning accuracy. But for the next 380,000 years, the universe remained a hot, dense, and opaque plasma. The temperature was still too high for the newly formed atomic nuclei to capture the free-roaming electrons. This sea of free electrons acted like a dense fog, constantly scattering the photons of light and preventing them from traveling any significant distance. The universe was a glowing but impenetrable haze. Then, as the universe reached the age of 380,000 years, it crossed another critical threshold. The temperature dropped to about 3,000 Kelvin, cool enough for the electrons to finally be captured by the atomic nuclei, forming the first stable, neutral atoms. This event is known as recombination or decoupling. Suddenly, the cosmic fog lifted. The universe became transparent to light. The photons that had been trapped in the primordial plasma were now free to travel unimpeded through the expanding space, and they have been traveling ever since. Their wavelength stretched by the subsequent expansion of the universe from the high-energy light of a glowing fireball into the cool, faint microwaves that we detect today from all directions in the sky. This is the cosmic microwave background, the oldest light in the universe, a beautiful and incredibly informative fossil of the infant cosmos. The CMB is not perfectly uniform. It contains tiny, almost imperceptible temperature fluctuations, variations of about 1 part in 100,000. These tiny anisotropies are the imprints of the initial density fluctuations in the primordial universe, the quantum ripples from the inflationary epoch that were stretched to astronomical scales. These fluctuations are the seeds of all cosmic structure. The slightly denser regions were the gravitational wells into which matter would later fall, the birthplaces of the first stars and galaxies. The slightly less dense regions would become the great cosmic voids. The CMB is a baby picture of our universe, a snapshot of the moment it first became transparent, a map of the primordial seeds from which the entire, glorious and complex tapestry of the cosmos would eventually grow. The period following the release of the cosmic microwave background, from about 400,000 years to a few 100 million years after the Big Bang, is known as the Cosmic Dark Ages. The universe was now transparent, but it was also dark. The primordial fireball had faded, and there were not yet any stars or galaxies to light up the cosmos. The universe was a vast, expanding, and slowly cooling expanse of neutral hydrogen and helium gas, with the tiny primordial density fluctuations sown by inflation gently growing under the influence of gravity. The Dark Ages were a time of quiet gestation, a period where the seeds of cosmic structure were slowly, patiently beginning to sprout. In the slightly denser regions of the universe, gravity began to win its long battle against the outward pressure of the gas. The neutral hydrogen and helium began to clump together, forming vast, filamentary structures, the first skeletal outlines of the cosmic web. The dominant gravitational player in this process was not the normal, baryonic matter, but the mysterious, invisible dark matter. Because dark matter does not interact with light, it was not coupled to the radiation pressure of the early universe. It was free to begin clumping and forming gravitational halos long before the baryonic matter. These dark matter halos acted as the gravitational seeds, the cosmic nurseries into which the normal gas would later fall. Over millions of years, the gas within these dark matter halos became denser and denser. As it was compressed, it began to heat up. But for a star to form, the gas must be able to cool, to radiate away its heat, so that gravity can continue its work of compression. The primordial gas of the Dark Ages, composed almost entirely of hydrogen and helium, was a very inefficient coolant. It took a long time and a lot of mass for a gas cloud to cool enough to trigger the first star formation. But eventually, in the densest hearts of the most massive of these early dark matter halos, the conditions became right. The first stars were born. The ignition of these first stars, known as population 3 stars, marks the end of the cosmic dark ages and the beginning of the cosmic dawn. These were not like the stars we see today because they formed from the pristine, metal-free gas of the early universe. They were incredibly massive, perhaps hundreds of times the mass of our Sun. And because of their immense mass, they were incredibly hot, incredibly luminous, and incredibly short-lived. They blazed with a fierce, blue-white light, flooding the surrounding darkness with the first starlight the universe had ever known. Their intense, high-energy ultraviolet radiation began to ionize the neutral hydrogen gas around them, creating expanding bubbles of ionized plasma in the surrounding dark. And their lives ended in spectacular, cataclysmic supernova explosions that seeded the universe with the first heavy elements, the metals that would be essential for the formation of the next generation of stars, of planets, and of life itself. These first stars were the pioneers, the cosmic trailblazers who lit up the darkness and began the long, complex process of transforming the simple, primordial universe into the rich, chemically diverse, and life-bearing cosmos we inhabit today. The birth of the first stars triggered a cascade of structure formation in the early universe. The dark matter halos that hosted these stars continued to grow, merging with their neighbors to form larger and larger structures. Within these halos, the gas, now enriched with the first heavy elements from the population 3 supernovae, could cool more efficiently, leading to the formation of the first protogalaxies. These were small, irregular, and chaotic systems, a far cry from the grand, ordered spiral galaxies we see today. They were the building blocks, the cosmic Legos, from which the larger galaxies would be assembled over billions of years. This is the hierarchical or bottom-up model of galaxy formation, the current standard paradigm in cosmology. In this picture, small things form first, and then merge to form bigger things. The early universe was a violent and dynamic place, a cosmic construction site where these proto-galaxies were constantly colliding and merging, triggering intense bursts of star formation. The James Webb Space Telescope has given us our first tantalizing glimpses into this chaotic early epoch. It has observed galaxies that were already in place just a few hundred million years after the Big Bang. Their light red-shifted into the infrared by the expansion of the universe. And these early galaxies are not always the small, messy objects our models predicted. Some of them appear to be surprisingly large, surprisingly massive, and surprisingly well organized, challenging our understanding of how quickly these structures could have formed. As these first proto-galaxies grew and evolved, their combined radiation, along with the radiation from the first quasars, began to have a profound impact on the universe as a whole. This was the epoch of reionization. The bubbles of ionized hydrogen created by the first stars and galaxies began to grow and overlap, until, by about 1 billion years after the Big Bang, the entire vast expanse of the intergalactic medium had been transformed from a cold, neutral gas back into a hot, ionized plasma. The universe, which had been dark and opaque during the Dark Ages, was now transparent and filled with light once again. This was a fundamental phase transition for the cosmos, a second coming of age that set the stage for the evolution of the large-scale structures we see today. The epoch of reionization was not a simple, uniform process. It was a patchy, complex affair, with some regions of the universe becoming ionized earlier than others, depending on the local density of stars and galaxies. Mapping this process in detail is one of the primary goals of modern cosmology, as it holds the key to understanding the nature of the first luminous sources and their impact on the cosmic environment. Observatories like the Square Kilometre Array are designed to detect the faint 21-centimeter radio signal from the neutral hydrogen of the Dark Ages and the epoch of reionization, which will allow us to create a three-dimensional map of this crucial transformative period in our universe's history. The story of the first stars and galaxies is a story of how, from the quiet darkness of a simple primordial state, the first points of light emerged, and how that light, in turn, transformed the entire cosmos, setting the stage for the rich, complex, and beautiful universe we now inhabit. It is a story of how the universe lit its own fire, a fire that continues to burn in the hearts of billions of galaxies, including our own. The galaxies we see in the universe today are not a random assortment of shapes and sizes. They fall into a surprisingly well-ordered classification scheme, a tuning fork diagram first developed by the great astronomer Edwin Hubble in 1926. This scheme, which is still the starting point for our understanding of galaxy morphology, divides galaxies into three main classes: ellipticals, spirals, and irregulars. Elliptical galaxies are smooth, featureless, and often spheroidal or football-shaped collections of stars. They are the old red and dead galaxies of the universe. They are dominated by old reddish stars. They contain very little cold gas and dust, and they have very low rates of ongoing star formation. They are the calm, stately, and retired citizens of the cosmic city. Spiral galaxies, like our own Milky Way, are the vibrant, active, and youthful members of the galactic population. They are characterized by a flat, rotating disk of stars, gas, and dust, with beautiful, elegant spiral arms where new, hot blue stars are constantly being born. They often have a central, spheroidal bulge of older stars, and many, including our own galaxy, have a central bar-like structure from which the spiral arms emerge. These are the barred spiral galaxies. Irregular galaxies, as their name suggests, are the misfits, the rebels of the cosmic zoo. They lack any clear, defined structure. They are often chaotic, clumpy, and rich in gas and dust, with high rates of vigorous and often bursty. Star formation. They are the cosmic works in progress, galaxies that are still in the process of being assembled or have recently been disturbed by a close encounter with a neighbor. The Hubble tuning fork is not just a classification scheme. It is also, in a rough sense, an evolutionary sequence. The current paradigm of galaxy formation, the hierarchical model, suggests that the chaotic, irregular galaxies of the early universe gradually, through a series of mergers and a long period of more quiescent evolution, transform into the grand and ordered spiral and elliptical galaxies we see today. The key driver of this transformation is gravity, which pulls together the dark matter halos, which in turn pull together the gas and the stars. But the story is not just one of gravity. It is a complex interplay of a host of different physical processes, a cosmic dance of feedback and regulation. The process of star formation itself is a powerful feedback mechanism. The intense radiation and powerful stellar winds from young, massive stars can heat and blow away the surrounding gas, inhibiting the formation of further stars. The supernova explosions that mark the end of these massive stars' lives are even more powerful. They inject a huge amount of energy and heavy elements into the interstellar medium, creating vast, expanding superbubbles of hot gas that can clear out entire regions of a galaxy, temporarily shutting down star formation. But this feedback is not just destructive. The shock waves from these supernovae can also compress the surrounding gas clouds, triggering a new wave of star formation. It is a self-regulating cycle of birth, death, and rebirth. On an even larger scale, the supermassive black holes at the centers of galaxies are now known to be crucial players in this cosmic feedback loop. As gas falls towards the central black hole, it forms a hot, luminous accretion disk, which can launch powerful jets and winds that can travel at nearly the speed of light. This active galactic nucleus feedback can be so powerful that it can heat and expel the gas from the entire galaxy, effectively quenching all future star formation. This is thought to be the primary mechanism that transforms large, star-forming spiral galaxies into quiescent, red and dead elliptical galaxies. The beautiful, ordered structures we see in the universe today are not a static, final state. They are the product of a long, violent, and complex history. A history of mergers, of starbursts, of feedback, of a constant, dynamic interplay between the creative force of gravity and the regulatory forces of stellar and AGN feedback. The universe is not just a collection of galaxies. It is a dynamic, evolving ecosystem, and understanding the intricate feedback loops that govern this ecosystem is one of the central goals of modern astrophysics. The evolution of a galaxy is not just determined by its internal processes. It is also profoundly shaped by its environment. A galaxy that lives a solitary life in the middle of a cosmic void will have a very different history from a galaxy that inhabits the dense, crowded heart of a massive galaxy cluster. This is the nature versus nurture debate of cosmology. The nature of a galaxy is its intrinsic properties, like its mass and its angular momentum, which are largely determined by the initial conditions of the dark matter halo in which it formed. The nurture is the influence of its environment, the interactions with its neighbors, and with the larger cosmic web. Both are crucial. An isolated galaxy, a cosmic hermit, can evolve in a relatively peaceful and quiescent way. It can slowly accrete gas from the surrounding intergalactic medium, fueling a steady, long-lived rate of star formation. This is the likely history of many of the beautiful, grand-designed spiral galaxies we see in the field. But a galaxy that lives in a dense cluster is subject to a host of environmental processes that can dramatically alter its fate. As a galaxy falls into a cluster, it moves through the hot, dense intracluster medium, the tenuous gas that fills the space between the cluster galaxies. This can lead to ram pressure stripping, where the galaxy's own interstellar gas is stripped away by its motion through the intracluster medium, like a runner's hair being blown back by the wind. This process can quickly remove a galaxy's fuel for star formation, transforming a blue, star-forming spiral into a red, quiescent S0 or lenticular galaxy. Galaxies in clusters are also subject to more frequent gravitational interactions. Tidal stripping can occur when a smaller galaxy passes close to a larger one, its outer stars and gas being torn away by the stronger gravitational pull of its massive neighbor. We see evidence of this in the long, beautiful tidal streams of stars that are often seen snaking around massive galaxies like our own Milky Way and the Andromeda Galaxy. These streams are the ghostly remnants of dwarf galaxies that have been tidally disrupted and are in the process of being accreted. And of course, there are the direct cataclysmic collisions and mergers. While these are more common in smaller galaxy groups, they can also occur in clusters, leading to the formation of the most massive galaxies in the universe. The giant CD elliptical galaxies that are often found at the very center of rich clusters. These cosmic behemoths are thought to be the product of multiple, repeated mergers over cosmic time. The environment of a galaxy, therefore, plays a pivotal role in its evolution, in a process that is sometimes called galaxy harassment. The dense, violent, and gas-poor environment of a cluster tends to transform star-forming spiral galaxies into quiescent elliptical and S0 galaxies. This is known as the morphology-density relation, a well-observed correlation in the local universe. The cosmic web itself plays a crucial role in this environmental story. The filaments of the web act as the cosmic highways along which galaxies and gas are funneled into the growing clusters at the nodes. Galaxies that live in the filaments are in a transitional environment, still accreting gas and forming stars, but also beginning to feel the gravitational influence of the nearby cluster. They are the suburban galaxies, on their way to the bustling and often brutal life of the cosmic city. Understanding the complex interplay between a galaxy's intrinsic nature and its environmental nurture is one of the key challenges in building a complete picture of galaxy formation and evolution. It requires a combination of large-scale cosmological simulations that can model the growth of the cosmic web and the formation of clusters, and high-resolution zoom-in simulations that can model the detailed, messy physics of star formation, feedback, and galactic interactions within individual galaxies. It is a monumental task, but it is one that is bringing us closer than ever to a complete and beautifully complex understanding of the origin and evolution of the magnificent star islands that we call home. Our own cosmic home, the Milky Way galaxy, and its nearest major neighbor, the Andromeda Galaxy, provide us with a unique and powerful laboratory for studying the processes of galaxy formation and evolution up close. They are the two largest members of the local group, a gravitationally bound collection of more than 50 galaxies, and they offer us a detailed archaeological window into the history of a typical large spiral galaxy. The Milky Way is a barred spiral galaxy, a vast rotating disk of about 100 billion stars, with a central bar-like structure and a number of spiral arms. We are located in one of these arms, the Orion Arm, about 27,000 light-years from the galactic center. By meticulously mapping the positions, motions, and chemical compositions of the stars in our galaxy, a field known as galactic archaeology, astronomers are able to piece together the story of its formation. We have learned that the Milky Way, like other large galaxies, was built up over billions of years through the hierarchical merger of smaller protogalactic fragments. The oldest stars in our galaxy are found in its stellar halo, a vast, diffuse, and spherical component that surrounds the disk, and in its central bulge. These stars are typically metal-poor, meaning they have a low abundance of elements heavier than hydrogen and helium, a sign that they formed early in the universe's history, before many generations of stars had had a chance to enrich the interstellar medium. The disk of the galaxy, on the other hand, is home to younger, more metal-rich stars, like our own Sun, and is the site of most of the ongoing star formation. The evidence for the Milky Way's merger history is written in the sky. We see numerous stellar streams, long, coherent trails of stars that are the tidally disrupted remnants of smaller dwarf galaxies that have been, or are currently being, accreted by our own. The Sagittarius Stream, for example, is a vast river of stars that wraps around the entire galaxy, the ghost of a dwarf galaxy that is being torn apart by the Milky Way's immense gravitational pull. These streams are the fossils of our galaxy's cannibalistic past, and by studying their orbits and their stellar populations, we can reconstruct the timeline of our galaxy's assembly. The Andromeda Galaxy, also known as Messier 31, is our cosmic twin, a slightly larger spiral galaxy located about 2.5 million light-years away. It is the most distant object that can be seen with the naked eye, a faint, fuzzy patch in the night sky, and it is on a collision course with our own. In about 4.5 billion years, the Milky Way and Andromeda will begin a long, slow, and spectacular merger, a cosmic dance that will, over hundreds of millions of years, transform the two spiral galaxies into a single, massive elliptical galaxy, which some have nicknamed Milkomeda. This future collision provides us with a real-time preview of one of the most important processes in galaxy evolution. But Andromeda also offers us a unique, external perspective on a galaxy that is very similar to our own, because we see it from the outside. We can study its overall structure, its spiral arms, its stellar halo, in a way that is difficult for our own dust-obscured galaxy. Observations of Andromeda have revealed a history that is remarkably similar to our own, with a vast stellar halo filled with the remnants of past mergers and a complex, clumpy disk that is still actively forming stars. The study of the local group, with its two giant spirals and its retinue of smaller, dwarf satellite galaxies, is a field that is rich with information about the processes of galaxy formation, of feedback, of tidal stripping, of mergers. It is our own local cosmic ecosystem, and by studying it in detail, with telescopes like Gaia, which is mapping the positions and motions of 1 billion stars in our galaxy, and the James Webb Space Telescope, which can peer through the dust to see the individual stars in Andromeda. We are piecing together the story of our own cosmic origins, a story that is both uniquely our own and also a beautiful and representative chapter in the grand, universal epic of galaxy formation and evolution. The luminous, baryonic matter that makes up the stars and gas of galaxies is only a small fraction of the total cosmic inventory. The vast majority of the matter in the universe, about 85% of it, is in the form of dark matter, a mysterious, invisible substance that does not interact with light. The story of galaxy formation is, in a very real sense, the story of dark matter. It is the dark matter that provides the gravitational scaffolding, the invisible architecture upon which the visible structures of the universe are built. The existence of dark matter was first inferred in the 1930s by the Swiss astronomer Fritz Zwicky, who observed that the galaxies in the Coma cluster were moving far too fast to be held together by the gravity of the visible matter alone. He postulated the existence of some form of Dunkel materia, or dark matter, to provide the extra gravitational glue. His idea was largely ignored for decades, until the 1970s, when the astronomer Vera Rubin made a similar discovery on the scale of individual galaxies. She meticulously measured the rotation curves of spiral galaxies, the speed at which the stars orbit the galactic center as a function of their distance. According to Newtonian gravity, the stars at the outer edges of a galaxy, where the visible matter thins out, should be moving much more slowly than the stars in the inner regions. But Rubin found that the rotation curves were flat. The outer stars were moving just as fast as the inner ones. This was a stunning result, and it provided the most compelling evidence yet for the existence of a vast, extended halo of invisible dark matter surrounding the visible disk of the galaxy. A halo whose gravitational pull was responsible for the high orbital speeds of the outer stars. Since then, the evidence for dark matter has become overwhelming. We see its effects in the gravitational lensing of distant objects by galaxy clusters, in the temperature fluctuations of the cosmic microwave background, and in the very existence of the large-scale structure of the universe. The cosmic web itself is primarily a web of dark matter. The standard model of cosmology is now the lambda cold dark matter model, where cold dark matter is the specific type of dark matter that is thought to make up the bulk of the universe's mass. Cold in this context means that the dark matter particles were moving slowly in the early universe, which allows them to clump together easily and form the small-scale structures, the dark matter halos that are the seeds of galaxy formation. The story of galaxy formation, then, begins with the dark matter. In the early universe, the tiny quantum fluctuations from inflation created small overdensities in the otherwise uniform distribution of dark matter. These overdensities began to grow under the influence of their own gravity, collapsing to form the first small dark matter halos. This is a hierarchical, bottom-up process. Small halos form first, and then, over cosmic time, they merge to form larger and larger halos. The normal baryonic matter is, at first, just a passive bystander in this process. But after the universe becomes transparent at the time of recombination, the baryonic gas is free to fall into the deep gravitational potential wells of these pre-existing dark matter halos. It is within these dark matter cocoons that the gas can cool, condense, and form the first stars and galaxies. The properties of a galaxy, its mass, its size, its shape, are thought to be largely determined by the properties of the dark matter halo in which it resides. The distribution of dark matter is not just a passive scaffolding. It is the genetic code that dictates the form and evolution of the visible galaxy. While the LCDM model has been remarkably successful in explaining the large-scale structure of the universe, it does face some challenges on smaller, galactic scales. The cusp core problem. The fact that the centers of some dark matter halos appear to be less dense than the cuspy profiles predicted by simple CDM simulations. And the missing satellites problem. The fact that we observe fewer small, dwarf satellite galaxies around the Milky Way than the simulations predict have led some to question the simple, collisionless nature of cold dark matter. These small-scale crises may be solved by a more sophisticated understanding of the messy baryonic physics of feedback, which can heat and expel matter from the centers of galaxies. Or they may be a hint that the nature of dark matter is more complex than we think. Perhaps dark matter is self-interacting, or warm, or has some other exotic property. The quest to identify the dark matter particle is one of the most urgent and exciting challenges in all of modern science. Experiments deep underground are trying to detect the faint, rare interactions of dark matter particles with normal matter. Particle accelerators like the Large Hadron Collider are trying to create dark matter particles in high-energy collisions, and telescopes are searching for the indirect signatures of dark matter annihilation in the gamma-ray sky. The mystery of dark matter is a puzzle that connects the largest structures in the cosmos with the smallest, most fundamental constituents of reality. And solving it will be a crucial step in completing our picture of how the magnificent islands of stars we call galaxies came to be. The story of galaxy formation and evolution is a story of immense complexity, a story that plays out over billions of years and involves a delicate and intricate interplay of gravity, gas dynamics, star formation, stellar feedback, black hole activity, and the mysterious influences of dark matter and dark energy. To understand this complex, multi-scale process, astronomers have turned to one of their most powerful tools, computational simulations. These are not just simple computer models. They are vast, virtual universes built inside supercomputers that attempt to replicate the entire 14 billion-year history of the cosmos, from the initial conditions of the Big Bang to the present-day distribution of galaxies. These cosmological hydrodynamic simulations are some of the most complex and computationally expensive calculations ever performed in science. They start with a large, representative volume of the early universe, filled with dark matter and baryonic gas, and with the tiny primordial density fluctuations predicted by the theory of inflation. The simulation then evolves this virtual universe forward in time, step by step, calculating the gravitational forces between all the particles, the complex hydrodynamics of the gas as it cools, collapses, and shocks, and the subgrid physics of star formation and feedback, which are too small scale to be resolved directly, but whose effects are crucial to the overall evolution of the galaxies. The results of these simulations are nothing short of spectacular. They produce virtual universes that look remarkably and often beautifully similar to our own. They show the hierarchical formation of the cosmic web, with dark matter collapsing into filaments and halos. They show the baryonic gas falling into these halos, cooling, and forming rotating disks of stars. They show the violent mergers of galaxies, the triggering of starbursts, the growth of supermassive black holes, and the powerful feedback from supernovae and active galactic nuclei that regulates the growth of the galaxies. Projects like the Illustris and Eagle simulations have been particularly successful in this endeavor. These simulations have been able to reproduce, with remarkable accuracy, a host of observed properties of the galaxy population, such as the galaxy mass function, the morphology-density relation, and the bimodal color-magnitude diagram. These successes have given us a great deal of confidence in the overall hierarchical LCDM paradigm of galaxy formation. They have shown us that our basic picture of how the universe is put together is, in all likelihood, correct. But these simulations are not just about confirming what we already know. They are also powerful tools for discovery. By comparing the detailed predictions of the simulations with the ever more precise observations from telescopes like Hubble and Webb, we can test our understanding of the complex subgrid physics of star formation and feedback. For example, by tweaking the parameters that govern the strength of supernova feedback or AGN feedback in the simulations, we can see what effect this has on the resulting galaxy population. And we can then compare this with the real universe to see which models work best. This is a powerful, iterative process, a dialogue between theory and observation that is constantly refining our understanding of the complex, baryonic processes that shape the galaxies we see. The simulations also allow us to do something that is impossible in the real world: to run the cosmic movie in reverse. To trace the history of a simulated galaxy back in time to understand its unique formation path. We can see which mergers were important, when it had its major bursts of star formation, how its central black hole grew. This provides an invaluable tool for interpreting the snapshots of real galaxies that we see at different cosmic epochs. Despite their immense success, the current generation of cosmological simulations is not without its limitations. They still struggle to accurately model some of the more subtle aspects of galaxy formation, like the structure of the thin disks of spiral galaxies or the abundance of the smallest, faintest satellite galaxies. And they are all, ultimately, based on the assumption that the underlying LCDM model of cosmology is correct. They are powerful tools for understanding the gastrophysics of galaxy formation, but they cannot, by themselves, tell us the nature of dark matter or dark energy. The next frontier for these simulations is to incorporate new physics to explore the consequences of different models of dark matter, of modified gravity, of dynamic dark energy. And as our computational power continues to grow, we will be able to simulate larger volumes of the universe at higher resolution, capturing the complex interplay between the small-scale physics of star formation and the large-scale environment of the cosmic web with ever-increasing fidelity. The virtual universes we build inside our supercomputers are becoming an indispensable tool in our quest to understand the real one. They are a testament to the power of our physical theories and a beautiful and dynamic illustration of the grand, complex, and magnificent story of how, from the simple primordial seeds of the early universe, the rich and wonderful tapestry of galaxies we see today was born. The story of galaxy formation is a story written in gas. This is the raw material, the lifeblood of the cosmos, the fuel from which stars are born, and the medium through which the great cosmic cycles of matter and energy play out. Understanding the journey of this gas, from the diffuse primordial soup of the early universe to the dense, star-forming molecular clouds of present-day galaxies, is the key to understanding the entire history of cosmic evolution. In the beginning, the baryonic matter of the universe was a hot, ionized plasma of hydrogen and helium. After recombination, it cooled and became a neutral gas, which then began to fall into the gravitational potential wells of the dark matter halos. As this gas was pulled in, it was shocked and heated to very high temperatures, forming a hot, diffuse corona around the growing protogalaxy. For a star to form, this hot gas must be able to cool and condense. The efficiency of this cooling process is what determines the rate of star formation in a galaxy. In the early universe, the gas was metal-poor, meaning it lacked the heavy elements that are efficient coolants. This made it difficult for the first stars to form. But once the first, population 3 stars exploded as supernovae. They seeded the surrounding gas with the first heavy elements. These metals allowed the gas to cool much more efficiently, triggering a new, more vigorous, and more self-sustaining cycle of star formation. The gas in a modern star-forming galaxy like the Milky Way exists in a complex, multi-phase interstellar medium. There is a hot, ionized medium, heated by supernovae and stellar winds. There is a warm, neutral medium, and there is a cold, dense molecular medium, where the gas is in the form of molecules like molecular hydrogen and carbon monoxide. It is in the coldest, densest hearts of these giant molecular clouds that new stars are born. This interstellar medium is not a static environment. It is a dynamic, turbulent, and constantly evolving ecosystem. Gas is constantly cycling between these different phases, driven by the feedback from star formation. But the gas in a galaxy is not a closed system. Galaxies are constantly accreting fresh, pristine gas from the intergalactic medium, the tenuous gas that fills the space between galaxies. This gas is thought to be delivered to galaxies along the filaments of the cosmic web, in a process known as cold stream accretion. These cosmic rivers of cold gas can penetrate deep into the dark matter halos of galaxies, providing a direct and efficient supply of fuel for ongoing star formation in the disk. This process is thought to be particularly important for fueling the high rates of star formation seen in galaxies in the early universe. At the same time, galaxies are also losing gas. The powerful winds driven by supernovae and active galactic nuclei can be so strong that they can expel gas from the galaxy entirely, launching it into the intergalactic medium in a galactic outflow. This process is crucial for regulating the growth of galaxies and for enriching the IGM with the heavy elements forged in stars. Some of this expelled gas may cool and eventually rain back down onto the galaxy in a galactic fountain. contributing to a cosmic recycling process that can sustain star formation over billions of years. The journey of the gas is a complex and beautiful one, a journey that connects the largest scales of the cosmos with the smallest, the intergalactic with the interstellar, the process of galaxy formation with the birth of individual stars and planets, and it is a journey that we are now able to trace with unprecedented detail. Thanks to a new generation of powerful telescopes, radio telescopes can map the distribution of cold, molecular gas. Optical telescopes can map the distribution of warm, ionized gas, traced by the characteristic red glow of hydrogen alpha emission from star-forming regions. And X-ray telescopes can map the distribution of the hot coronal gas. By combining these different views, we are beginning to build a complete, multi-wavelength picture of the complex, gaseous ecosystem of galaxies, an ecosystem that is the ultimate source of all the structure, all the complexity, and all the life in the universe. The intricate interplay between dark matter and baryonic matter is at the very heart of the story of galaxy formation. Dark matter provides the gravitational scaffolding, the invisible architecture upon which the visible universe is built. But it is the baryonic matter, the gas, the stars, the dust that brings this architecture to life, that creates the light, the color, and the complexity of the galaxies we see. The relationship between these two components is a complex and dynamic one, a cosmic dance that has shaped the evolution of the universe for the past 14 billion years. The dance begins in the early universe. Dark matter, being collisionless, is able to start clumping together early on, forming the first small halos. Baryonic matter, on the other hand, is coupled to the radiation field, and its pressure prevents it from collapsing until after the universe becomes transparent at the time of recombination. After this point, the baryons are free to fall into the pre-existing dark matter halos. But the baryons are not just passive followers, they have their own rich physics. The gas can cool, it can radiate away its energy, and it can collapse to much higher densities than the dark matter. This is why the visible, baryonic part of a galaxy is typically much smaller and more concentrated than its vast, diffuse dark matter halo. The process of star formation and the subsequent feedback from supernovae and active galactic nuclei are purely baryonic processes, but they can have a profound impact on the distribution of the dark matter. The powerful outflows of gas driven by feedback can heat and expand the inner regions of a dark matter halo, potentially softening the central cusp that is predicted by simple, dark matter-only simulations. This baryonic feedback is one of the leading potential solutions to the cusp core problem, one of the small-scale challenges to the standard LCDM model. The relationship between the mass of a galaxy's stars and the mass of its dark matter halo is a crucial diagnostic for our models of galaxy formation. Observations show that this relationship is not a simple, linear one for both very low mass and very high mass halos. The efficiency of converting baryons into stars is very low. In low mass halos, supernova feedback is thought to be so efficient that it can blow most of the gas out of the shallow gravitational potential well, quenching star formation. In very high mass halos, the gas in the corona is so hot that it cannot cool efficiently, and AGN feedback is thought to prevent the gas from accreting onto the central galaxy. It is only in halos with a mass similar to that of our own Milky Way that the star formation efficiency reaches its peak. This Goldilocks effect is a beautiful example of the self-regulating nature of galaxy formation, a process that is governed by the complex feedback loop between the baryonic physics of the galaxy and the gravitational potential of its dark matter halo. But the dance between dark matter and baryons is not just about feedback. It is also about the large-scale environment. In the dense heart of a galaxy cluster, the hot X-ray emitting gas of the intracluster medium can strip the gas from a galaxy, But the dark matter, being collisionless, is unaffected. This can lead to a separation between the baryonic and dark matter components of a galaxy, a process that we can observe directly through a combination of X-ray and gravitational lensing observations. The famous bullet cluster, a system of two colliding galaxy clusters, is the poster child for this effect. The hot gas from the two clusters has collided and shocked, creating a bullet-shaped cloud of X-ray emitting gas, while the dark matter from the two clusters, which we can map through its gravitational lensing effect, has passed right through each other, seemingly unimpeded. This is some of the most direct and compelling evidence we have for the existence of collisionless dark matter. The intricate and often violent dance between the visible and the invisible, between the baryons and the dark matter, is a story that is still being unraveled. It is a story that requires a combination of large-scale cosmological simulations, high-resolution observations across the entire electromagnetic spectrum, and a deep theoretical understanding of the complex physics of the baryonic ISM. But it is a story that is at the very heart of our quest to understand how the universe we see today, with all its beauty and complexity, emerged from the simple, primordial ingredients of the early cosmos. The future of our universe, once a topic reserved for theologians and philosophers, has become a field of active and precise scientific inquiry. The discovery of dark energy and the accelerating expansion of the cosmos has provided us with a new, and in many ways, more definitive, picture of our ultimate cosmic destiny. And it is a picture that is, for the most part, a cold, dark, and lonely one. If dark energy is a true cosmological constant, an unchanging energy of the vacuum itself, as our current observations suggest, then the universe is destined for a big freeze or heat death. The accelerating expansion will continue forever. In the coming billions of years, galaxies beyond our own local group will recede from us at ever-increasing speeds, eventually crossing our cosmic event horizon and disappearing from our view forever. The night sky of the distant future will be a dark and empty place, containing only the aging stars of our own merged Milky Way galaxy. Over much longer timescales, on the order of trillions of years, the process of star formation will cease. As the gas reservoirs of the galaxies are exhausted, the universe will enter a degenerate era, a time when the only objects left are the cold, dead remnants of stars, white dwarfs, neutron stars, and black holes. Even these objects are not eternal. Over even more immense, almost unimaginable timescales, on the order of 10 to the power of 40 years, protons themselves are predicted to decay, causing the white dwarfs and neutron stars to slowly dissolve into a sea of radiation and leptons. The only objects left will be the black holes, and even they are not forever. Due to Hawking radiation, black holes will slowly evaporate, their mass converted into a faint, thermal radiation. The supermassive black holes at the centers of galaxies will be the last to go, taking perhaps as long as 10 to the power of 100 years to evaporate completely. After this black hole era, the universe will enter its final, eternal state, the dark era. It will be a cold, dark, and almost perfectly empty void. A universe filled with nothing but a diffuse, ever-cooling bath of photons, neutrinos, and a few stray electrons and positrons. It will be a universe in a state of maximum entropy, a state of heat death, where no further thermodynamic work is possible and nothing ever happens again. This is a bleak, but scientifically plausible, vision of the ultimate fate of our cosmos. But what if dark energy is not a constant? If dark energy is a phantom energy whose density increases over time, then the future is far more violent. This leads to the Big Rip scenario. In this case, the accelerating expansion will become so powerful that it will eventually overcome all the other forces of nature. In the final moments of the universe, The repulsive force of the phantom energy will first tear apart galaxy clusters, then galaxies, then solar systems, then planets. And finally, in the last fraction of a second, it will overcome the strong nuclear force and rip apart the atoms themselves, reducing the entire cosmos to a shower of fundamental particles, each forever isolated in an infinitely expanding void. On the other hand, if dark energy is a dynamic quintessence field that could one day decay or change its sign, then the future could be very different. The acceleration could stop, and the universe could even begin to contract, leading to a big crunch, a fiery mirror image of the Big Bang. This opens up the possibility of a big bounce and a cyclic universe, an endless, self-renewing cosmos with no ultimate beginning or end. Distinguishing between these different fates is one of the primary goals of future cosmological observations. By precisely measuring the expansion history of the universe and the properties of dark energy, we can hope to determine whether our cosmos is destined for a slow, cold death, a violent, fiery rip, or an eternal cyclical rebirth. This is a quest that is not just about science. It is about our own, deepest existential questions. It is about understanding the ultimate context of our own brief and precious existence in a universe whose grand cosmic story we are only just beginning to read. The story of the universe, from its fiery birth to its potential cold demise, is a story that has been pieced together through a long and arduous process of scientific inquiry, a process that is a testament to the power and the beauty of the human mind. It is a story that has taken us from the Earth-centered cosmos of the ancients to the vast, expanding, and mysterious universe of modern cosmology. And it is a story that is far from over. We are living in a golden age of discovery, a time when a new generation of powerful telescopes and experiments is poised to answer some of the longest-standing questions in science, and to open up new, unforeseen avenues of inquiry. The James Webb Space Telescope is already providing us with our deepest and sharpest views of the infant universe, revealing the first galaxies as they form from the primordial darkness. Future gravitational wave observatories, like the Laser Interferometer Space Antenna, will allow us to hear the universe, to detect the faint space-time ripples from the mergers of supermassive black holes, and perhaps even from the moment of cosmic inflation itself. New large-scale galaxy surveys will map the cosmic web with unprecedented detail, allowing us to trace the history of cosmic expansion and to probe the mysterious nature of dark matter and dark energy. And on the theoretical front, the quest for a unified theory of quantum gravity, a theory of everything, continues. A quest that promises to reveal the deepest secrets of space, time, and the very nature of reality. But for all our progress, for all our powerful theories and our magnificent instruments, we must always remember the profound wisdom of learned ignorance. The more we learn, the more we become aware of the vast, uncharted ocean of our own ignorance. The universe is not a simple puzzle to be solved, but a deep, and perhaps infinite, mystery to be explored, to be wondered at, to be lived. Every answer we find seems to lead to a new, deeper and more beautiful question. The mysteries of the quantum vacuum, of dark energy, of the origin of the arrow of time, of the nature of consciousness itself. These are not just problems for scientists. They are invitations to all of us, to a state of wonder, of curiosity, of humility. They are a reminder that the world is far stranger, far more beautiful, and far more mysterious than our everyday experience would lead us to believe. And as we stand on the shore of this great cosmic ocean, we are not just passive observers, we are the universe's own way of knowing itself. The atoms in our bodies, the consciousness in our minds, are a direct and unbroken lineage from the fiery heart of the Big Bang. We are stardust, animated by the same mysterious life force that has driven the universe's long and magnificent journey from simplicity to complexity. And the quest to understand this universe, this home, is the noblest and most meaningful adventure that we, as a species, can undertake as you close your eyes and prepare for the quiet, restorative journey of sleep. You can feel a sense of participation in this grand, human, and cosmic story, the consciousness that is about to drift into the timeless, mysterious, and creative realm of dreams is the same consciousness that has dared to look up at the stars, to ask the biggest questions, and to begin, however tentatively, to read the silent, beautiful, and endlessly fascinating story of the cosmos. Good night, and may your dreams be as vast, as mysterious, and as wonderful as the universe itself.